से स्वागत। विशेष करके आज हमारे बीच उपस्थित मुख्य वक्ता सुश्री अनुराधा टीके, जिन्होंने हमारे इस अनुरोध को स्वीकार किया कि आज हमारे साथ आप जुड़ें और विद्यार्थियों को भारतीय अंतरिक्ष कार्यक्रम के बारे में विस्तार से बताएं। हम हमारे जो शासी निकाय के अध्यक्ष प्रोफेसर वी.एस. चौहान जी हैं, उनका भी हृदय से स्वागत करते हैं कि आप अपने व्यस्ततम क्षण में, आज आपको हैदराबाद में होना चाहिए था लेकिन आपने हमारे लिए समय निकाला और आप हमारे बीच उपस्थित हैं। सभी वैज्ञानिक गण, हमारे संस्थान के सभी इंजीनियर्स, विद्यार्थीगण और आज इस कार्यक्रम में प्रतिभाग कर रहे स्कूल से विद्यार्थी, आप सभी का स्वागत है। I would like to make a small presentation. It is a small, but it is very difficult to accommodate all the activities in a short period of time, 15 minutes, to give a good glimpse of what we are actually involved in and what we did during this academic year. So I'll make a small presentation. So you know that this center is the first of its kind, and it is operational round the clock and is available for most of the users across the country, whosoever has any interest in accelerator-based research. We have a systematic way of functioning, and this calendar of events are adhered to very strictly, and you could see many such activities in which we go to the universities, to the institutions where we organize acquaintance programs, and also we organize schools, workshops to provide a kind of hand-holding to the beginners and also to give a good glimpse of what activities they can participate in. So almost all the activities during the pandemic were organized as per the scheduled events and also online. So this is one such thing which we keep pursuing aggressively to make our footprint all over the country. As you see, we have, despite the fact that experimental facilities are challenged because of non-presence of the users, you could see here this accelerator user committee, which is actually was scheduled on 15th, 16th, 17th, 18th of this month, concluded yesterday. You could see number of proposals is always like, we thought that it will go down due to pandemic, due to non-availability of our users on the campus. But in all such activities, wherever we have invited proposals, the proposals have just crossed the limit which we had. So we are oversubscribed. We cannot offer to most of the users, but we are also making our best efforts so that whatever we offer them is available to our users. So you could see here 138 proposals were received. If you compare it last year and also the last to last year, this is a quite big number as compared to the earlier years. So this is what we see, and this time we thought that we should go for face-to-face. So we had a survey from all the users, but the survey was in the favor of online mode. You could see 73% people opted that they will be participating in online mode. So we have only arranged a lunch after this online activity, but I feel that from next year, when the pandemic slows down, we'll definitely have a face-to-face activity. You see how we have grown over the years and how these participations from different universities, different colleges, different institutes has kept swelling from one year to other year. And in terms of publications, in terms of our footprint across the country, it is all due to the hard work of our dedicated staff, dedicated engineers, dedicated scientists who make their efforts, the best efforts, to keep the people happy when they are performing the experiments. When I say happy means there is no disruption And if there is a disruption, we are there to attend the call even during the wee hours, which is generally not possible otherwise. So we started with the workhorse, which is Pelletron, and we have added many accelerators. And all these accelerators with the original sanctioned strength, they are operated optimally. You could see here, and the students who are participating today, they can have a virtual tour also. So this is the Pelletron, which we see in our brochures, the tower which is there. It was augmented further with the help of these cavities that are LINAC, linear accelerators, and many other accelerators, for example, for Rutherford backscattering, for dedicated AMS, and also ECR positive ion, MC SNCS. These are some of the other accelerators which are catering to the other needs of the users. If I talk about our workhorse performance, and I'm comparing this because these 2 years were challenging, 1920 and 2021, you could see due to our dedicated efforts, the maximum terminal potential was 15 MV during 1920, and now it could be achieved up to 14.88. But the most of the beams that were required by the users was made available, and we had to go for several cycles of conditioning for scheduled maintenance. Some of the maintenances were unscheduled because of breakdown, and you could see the numbers. I'm just comparing from 1920 to 2021. They're all comparable, and we are operating an optimal sort of operational values. So there were certain issues, and these issues were handled despite the fact that physical distancing were to be maintained and people were not allowed in a group inside the tank. But all these breakdowns were resolved, and we also did some maintenances in terms of replacements of column support post, and also the foils, the strippers which were required for getting good stable beam. This is about MC SNCS, the iron source. This was also maintained, and although because of I'm referring quite a few times that we were challenged due to severe COVID, and we all worked together so that there was no disruption except for the period when there was a complete lockdown. So my team was working with all dedication to keep the facilities operational. And I'll talk about the other activity, which is clubbing this superconducting LINAC. That also operated in 1920, and also it is still operating. It had to be operated, aborted because of the pandemic, but you could see all the experimental facilities in the beam hall 3 were given sufficient energetic beams, and many of the experiments could be performed during January to March 2020 when this campaign was on. If I talk about March, April 2021, or if I talk about October 2021, which is still continuing, and it will go for scheduled maintenance after this campaign is over. You could see, except for one cryostat, we can claim that the energy which was required by many users was sufficient to get good science out of this. So this is what we did, and we also keep our quarter wave resonators maintained, and this was heat treatment, and you could see the performance is optimal for these activities as well. So this is backed by cryogenic activities, and we could do a lot of work for providing the liquid helium, the gasifiers for a variety of purposes, be it MRI test, be it LINAC cool down. So for all the 2 runs which we had during this assessment period, we had a good impact of cryogenic facilities on operations of LINAC. We also did some developments relating to cryogenics, and the time is not permitting me to list all these activities, but to keep people motivated, to keep them engaged, it is my duty to highlight those things which are to be highlighted in presence of the participants and also in the presence of the distinguished guests today. This is another facility which is Rutherford backscattering, and there were some changes due to maintenance issues, but we did about 2,600 measurements for 50 users from different universities. So, these facilities are sometimes they require updation. So we are in the process of changing the data acquisition system and also adding negative ion source. As far as the statistics is concerned, the users were satisfied because whatever they wanted for different purposes, be it RBS, be it ERDA or channeling, the users 49 measurements about 816 comprising of 22 institutes were carried out during this January to April and June to October. The other important activity which we are involved in, we are setting up a high current injector, decouple the pelletron so that the nuclear physics community can be served without any hindrance. And this part is also taking a good shape. And all these components which are there for this high current injector, you could see here visibly that are all in place, and we tested it for the design as well as what we got. So you could see the design energy gain which was expected is also achieved during this period. So we are now in the process of getting this HEBT completion, and also we are going for higher A by Q. We did it for lower Q, but definitely the design is to be further tweaked, and also some of the modifications will be required for higher A by Q. So in the first phase of measurements, we also employed one of the Vajra faculty, and he did put some of his efforts for longitudinal diagnostics, and that is still going on. So we are in the process of augmenting the facilities in terms of diagnostics and also in terms of envisaged A by Q, so that after HEBT is implemented, it directly feeds the LINAC. So there is a fixed dependency on pelletron. Pelletron will be exclusively used for other purposes where we have a large number of people waiting in queue. This is about National Geochronology Facility. All the whatever you see here in this slide, they're all operational facilities, and they are used heavily by, I say heavily because this is a growing field where IUAC is supporting the community in a big way. So be it C14 measurements using 500 kilovolt ion accelerator, or XCAMS, or this HRSIMS, which has just been commissioned in December 2021, opening up many areas, starting from cosmochemistry to stable isotope geochemistry to trace elements to nuclear safeguard and forensic studies to depth profiling to deep earth processes. You can have geochronology besides cosmochemistry, because many other things are still to be explored by the geologists of this country. So that is a major activity which IUAC has taken up as a funded project from MOES, and we are going to set up another second campus of IUAC in Noida. Very soon it will also. You could appreciate some of the results which we have seen, comparing it with the ICP-MS with HRSIMS, how well we can go closer to the reported age with the help of this age which is determined, or the chronology found with HRSIMS. So zircon distillation, having isotope zircon distillation makes it possible that you can go to billion years as well. So without target, you cannot do experiments. Experiments heavily depend on the targets, and the target lab is again another lab which need mention, is special mention, because unless otherwise the users get the target, they cannot do the experiment. So a special mention is being made for this particular group. Now, coming to the other activities, I will summarize some of the things which we did in as a research activity. This HIRA spectrometers were used extensively during this period, and you could see the number of publications and also the number of experiments which we performed. So you see here this heavy ion reaction analyzer and hybrid recoil mass analyzer. In this particular effort using HIRA, we studied the effect of target deformation, how this compound nucleus is formed, and some of the important activities were noticed that evaporation residue cross sections at sub-barrier energies are larger in case of deformed target nucleus. So this was one such good experiment, and still we are carrying out some of the experiments these days. In HIRA, effect of proton shell closure, those who are well versed with the shell model, that can be good help to understand what we achieved in these two experiments, where compound nuclear formation and also having similar, etc. This was earlier done with some other target, and we got some exciting results there. And this year also, this manuscript has been submitted in HIRA. We also do simulations to corroborate the theoretical aspect and also have some insights into the experiments. So this was another achievement which is being encouraged. If you don't get beam time, even if you can do some simulations, provided you understand the physics underlying that process. The second component is Indian National Gamma Array. Is a beautiful explanation of how you can optimally utilize the resources, taking detectors from different parts of the country by participating many institutions. And this also has a very good coverage in terms of nuclear structures. And you could see a variety of the structures people study here. And many such publications came during this year, studying the structure, chiral rotations of vibrations, wobbling bands, symmetry of current loops, exploration of octopole, coexistence of different shapes. So these are some of the processes which you can always study, whatever energy available with us, provided the detectors are efficient. So this is INGA. You could see the detectors which are here. And then this is one such result which we reported was multiphonon transverse wobbling in barium, and that was published this year. Coming to the third aspect of nuclear physics is neutron detectors, and we focused on systematic study of reactions, probing the dynamics of fission mechanisms, and we look for experimental signatures and what are the parameters that influence, for example, excitation energy, angular momentum, entrance channel, mass symmetry. And you could see the detectors, and there's one such mention of a publication which came out with this particular facility. So I'm not going to give the details, but this is all available. And when you are going to interact with the scientists during this day-long activity, you can get some idea if you have any interest. In atomic and nuclear physics, we have two beam lines, one in low energy ion beam facility at 75 degree and another one is 105 degree. And we are augmenting this beam line by having several detectors for especially for X-ray emission. And we are in the process of building ion trap, which will again give some exciting studies. In material science beamline, a variety of equipment, facilities, which I'm not going to read, is all available. And this was extensively used by many of the users across the country. About 15 users experiments spread over 51 shifts have taken place. And if I talk about International School on Ion Beams in Material Science, 6th International Conference on Ion Beams in Materials Engineering and Characterization, School on ECR, ion source. So these are some of the glimpse. I have included the screenshots in this particular, but in many other workshops which were organized by other groups of our center, it is a kind of glimpse. You cannot repeat the same thing everywhere. if you see the beam times using Pelletron, the 21 runs having 68 shifts, different categories of BTRs were tested, and IUSC students, they won awards. Is again not limited only to IUSC students working in material science, but other students from other beam lines and also other disciplines, they also got recognized for their good work. So this is what I can summarize here for international and national conferences to give some kind of an encouragement to the IT sector of my center, where I guess the slides are now not visible. So I will conclude here. So I could not find time to mention about the terahertz facility. We had this time the signature of dark current, and we are in the process of commissioning this facility so that you can get terahertz as well as electron beam. The last important activity is about the MRI project, which is funded by MIT. First time in the country, we are attempting to have our own magnet based on superconductors, and this is also making a good progress. The bobbin is available. It has now been winding is being done. Cryostat, which is to be integrated, is already there. Is waiting for fabrication. The moment we get bobbin from after winding, we will take this further. So we created one group for catering to the AC accelerators, and that is low-level RF and bunching group. They have also done some developmental activities, and I am tempted to show you again this slide, because there is one important activity which I cannot leave without showing, and that is indigenous Atmanirbhar Bharat. You could see right from the very beginning, from 1996 to till date, we have developed a large number of components, large number of systems, subsystems to cater to the requirements of the center, so that import substitution is a possibility, and also developing in-house capability to maintain, to improvise. So that is all. So you can see here A1, and I have given the number serial number 1 to serial number 34. So there are 34 slides. I did not get time to include all of them, but you could see many such things which are developed in-house, and that is helping all the groups. And the downtime is less just because we have that kind of robust mechanism by which we attend all these issues immediately. So thank you very much for giving this opportunity, and all the thanks goes to the staff, the dedicated scientists, engineers of this center, who has made this Foundation Day memorable for me, because I am presenting on their behalf about the activities, even though the center was challenged, the experimental facilities were challenged because of pandemic. So in essence, I can say that pandemic had no impact on the functioning and operation of the facilities which we have here in IUSC. So thank you very much for all the good efforts, and I'll request Honorable Chairman Governing Board to acknowledge the good work done by our staff members. Thank you very much. I'm sorry I just exceeded. I cannot skip, and I did skip many of the things which was not possible to include in this short presentation.
Thank you, sir. Thank you, Professor Pandey, for your comprehensive and informative report on the activities of IUSC. Thank you, sir. So now may I request Professor V.S. Chauhan, Padma Shri, Arturo Falaschi Emeritus Scientist, J.C. Bose Fellow, and former Director, International Center for Genetic Engineering and Biotechnology, ICGEB, New Delhi, and present Chairman, Governing Board, IUSC, to kindly deliver the presidential address.
So Dr. Ghosh, I will take I will seek an opportunity to introduce Dr. Chauhan to the students.
Sure, sir. Please.
And also, Dr. Chauhan should be unmuted because he has been muted and that is locked. He cannot do it on his own. So for the students, those who are participating in this particular program, I take this opportunity to introduce Professor Chauhan, who did his bachelor's, master's and doctorate degree in chemistry from Delhi University. He won the highly prestigious Rhodes Fellowship Scholarship in 1974 to study at Oxford University, where he obtained a TPhil degree in 1977. After he returned to India in 1979, he started his career as a teacher. He taught at St. Stephen's College, then at IIT Kanpur, and then Delhi University. In addition to this, his brilliant academic record, he has also been an outstanding sportsman and he has represented Delhi University. Why I emphasize this? Because the most of the students, they don't go outside, they don't go for any sports activity. तो उन्होंने कभी हारना सीखा ही नहीं है और हारना सीखना हमको आना चाहिए. स्पोर्ट्स जब करते हैं आप तो रोज आप हारते हैं और अगले दिन आपके अंदर वो इच्छा होती है कि हम कल जीतेंगे, आज हमने ये मैच हारा तो कल हम जीतेंगे. लेकिन जो आपकी ये रोज कोई पेपर लिखना है, कुछ करना है, उसमें आप हार गए तो आपको निराशा होती है. तो मेरा मानना है कि प्रोफेसर चौहान से और यही आईसीजीबी में है और ये दौड़ते हुए इस उम्र में संजय वन में दिखाई पड़ते हैं when he goes to his residence. So we here sitting in IUSC don't go outside for a walk. So this is one important aspect which we need to emphasize. The second important thing is that you can do wonders while staying in India. It is not required that you have to go abroad, then only you can do wonders. So in 1988, he joined the International Center for Genetic Engineering and Biotechnology, where he became director. So he started his career from where and where he reached. You could see he also became chairman of UGC. He served in a brief stint of his chairmanship very brilliantly to help the higher education system at large. So he's a distinguished, internationally recognized scientist of India. His research interests are in fields of infectious diseases. विशेष करके तब हम जब आज कोविड की बात करते हैं, he was working with malaria vaccine and drug development and in study of peptides of biological importance. Scientific interest includes advocacy in infectious diseases, particularly TB and malaria. So he has published more than 270 research papers and guided more than 55 research students. He is an elected fellow of all the academies in India. He has been deeply involved in human resource development through major involvement in selection process of highly prestigious scholarships, including the Rhodes Fellowships, the INLACs and Felix Scholarships for Indian students to study abroad. Helping the students, those who have the spark, they can get the best avenue, and that is what Professor Chauhan's passion is. He has received many prestigious national awards and international awards and civil honors, which Dr. Shubhendu Ghosh has already mentioned that he was honored Padma Shri in 2012. He is a member of core committee of National Institute Ranking Framework. He worked as executive chairman of Executive Council of NAC. And I will not I can go on and on, but this is enough. And Professor Chauhan will forgive me for giving this much of long introduction. He is visiting scientist at ICGB, he is a J.C. Bose Fellow and Distinguished Biotechnology Research Professor. So I have taken much of your time, sir. So you have to do justice to the students. That was important, and because of that, I took this much of time. Thank you, sir. Welcome you for this.
Sir, sir, Professor Chauhan, that you have to, now the request has been sent to you, so please, you can unmute yourself now. The request already has been sent to you. Abhishek, could you please send the request another time to Professor Chauhan, please? Abhishek?
It will look like that I purposely eaten the time of Professor Chauhan by muting him. So kindly do it.
Sir, already the request you can see, it will pop up on your screen on your right hand side. Sahu, could you please help Professor Chauhan to unmute himself?
इजी क्यों
Sahu?
नहीं कर देते आप? सॉरी सर, सॉरी चौहान साहब को आप यहीं से क्यों नहीं कर देते? आईसीटी वाले लोग.
Hello. So the request has already been sent to Professor Chauhan, but I don't think he's there.
दोबारा एक बार भेज दो ना, और एक बार भेज दो. It will pop up in his screen,
I
right?
sent it.
चौहान साहब एक बार प्लीज देख लीजिए, आपको अनम्यूट माई सेल्फ करके कुछ बटन खोला होगा, कुछ पॉपअप हुआ होगा स्क्रीन में. यस.
Can you hear me now?
या
Yes, sir.
परफेक्ट.
अच्छा चलिए मैं बहुत जल्दी से बोलूंगा थोड़ा सा, but डायरेक्टर साहब thank you very much for the long introduction. उतना तो I don't deserve, but I'll make just 3 very brief points. When I've been associated with inter-university centers for quite a while. But before I say that, first of all, let me welcome all of you. Thank you very much. I'm a little bit nervous because the time is short and I don't want to delay all the further proceedings. Avinash has already given a very good snapshot of what is possible. I only, reflect back. I started my career way back in 70s, teaching career. So the people, and we rightly talk about Atmanirbharta, but a country which is, developing country, British didn't leave very much behind when they left. There were hardly any infrastructure. So over the years, when such decisions are taken, I often wonder, those who were taking this decision that we need this, we should have a University Grants Commission, and so on. I watched this happen, and I always marvel at the policymakers all through my career. So when inter-university centers were set up, what were the vision of people who did set them up? I really want to remember all of them for having thought they did. When I was briefly chairman of UGC, we did a review, and I took then the Minister Shri Prakash Javadekar with me to Pune, and we had all the 3 major and other centers come in one place in Pune. And we seriously looked at it. I didn't think in the country anywhere there were anything which was more cost effective as far as I could see, especially when it came to small centers of 20 acres or 15 acres space. There might be some other bigger concerns which spend money better. I was quite amazed the number of people who benefited from this continuously. And all 3 centers, we looked at Indore, Pune, and Delhi, did better than each other. And the minister was really agog. And sometimes I feel we did not advertise from the University Grants Commission enough of what the possibilities are. But when you review them now, when you have a look at them and what Avinash just now said, then you realize, as Avinash has already said, there are tremendous possibilities in India itself. But to make these facilities one thing, but to run these facilities, mostly in service mode, is just an outstanding job that these centers do, and many other centers. So I think what I want to say is the people who serve in these places, the scientists who serve, the people who make equipment, people who make them run 24/7, as Avinash said that COVID didn't affect you, Avinash, because you have dedicated people. If you didn't have dedicated people, I could have also stayed home. There's a pandemic. And I think this is the time on a foundation day to remember that the students who are listening to this and to the special invitee who will give a lecture, some of you, I hope most of you, get into teaching research careers. just remember to appreciate those who make your research possible. And they do it quite selflessly. And I can say that with greatest of clarity because I know Delhi Center, Pune Center, Indore Center very well. I've seen over the past decade now, met them many times. And I can't say enough how selflessly these people continue to work. And in addition to that, they produce good quality research. So I don't think you can't get any better deal than what you get in these centers.
तानिया
Yeah,
से हो गया मेरे पास एक लिंक आया था मैंने उसको हटा दिया तो ये है।
the other thing that I wanted to quickly grab is the
नहीं इधर ही है इधर ही है भैया, इधर ही है भैया, इधर ही है। हाँ
Please mute yourself.
somebody has to mute. But I'm going to stop very soon. So I'm absolutely delighted that you're having your foundation day. But Avinash, you did mention because I had connection problem for a while, that you have very impressive expansion plans also. And those expansion plans, when they set up, then the possibilities will increase. So the younger people who get into research, let's say next 5 years or 10 years, have research career, they will be, if not spoiled for choice, but they certainly would have so much access to good quality basic materials. They wouldn't have to run around to other countries. They're welcome to go and have exposure. But I dare say, and I can very quickly take you to my field. For example, today, and I speak this to the younger people. For example, if you want to be a vaccine researcher for future, you want to make vaccines for future pandemics or diseases for which there are no vaccine, like respiratory syncytial virus and many others, HIV. There's no country which is better placed to do that kind of development. You have outstanding industry. You have very clever molecular biologists and cell biologists. You have many, many institutions to go to. And these things, the whole world will end up looking towards India to provide those breakthroughs. I can assure you from my own experience, some of the vaccines that are being discovered for future, for the diseases like malaria, etc., their production, initial production is being done in India, either in Pune or in Hyderabad or in Bangalore. So the younger people who are there, I think you have so much more to look at. But as Avinash said, I would just say at the last, but then please don't do all by means hard work. Without hard work, you'll get nowhere. I mean, you may think a lot of people you look up, they're very successful. Virat Kohli is a very good batsman, or PV Sandhu is good, or Srikanth is in the final of badminton. But if you follow any of these stories of anybody, you will see that a trail of blood and sweat. So there is nothing you're going to achieve without very hard work. But hard work must be juxtaposed with a great sense of fun. If you don't enjoy what you do, I think it's not worth doing. So I still go to lab every day simply because I really enjoy it. So sense of fun in the lab, in the work, in your daily doing must not be compromised as well. I have to work, I have to get this award, I have to do this. I think that's not the idea of science. The idea of science is to enjoy it. And if you make up your mind, you will enjoy it. You will get paid for doing something that you'll enjoy. So I'm not going to take too much more time. I'm desperately waiting to listen to Anuradha. And I'm so glad, Avinash, you thought of her to give this talk. And I hope I'm not, gender sensitive or insensitive at all. But I hope soon you'll have a woman director of your institute. I hope I see that happen in my own time. So we desperately I'm seriously looking forward to your lecture, Anuradha. And I'll stop here. Once again, finally, I want to say, just remember, a lot of people who support, not only as scientists, but technicians, guards, people who feed you, or people who look after your gardens, I think they are no less important than the director. wherever you reach in your life, always remember there are lots of people who support you to be successful. I have never forgotten that. And I think you should keep that in mind, that without huge support from sacrifices from lots of people who work seemingly below you are no less important than you yourself. Thank you very much. Avinash, over to you.
Thank you, sir. And you could see the dedication. We have Dr. Amit Rai, who is joined us, Dr. Kanji Lal, and also all the associates of this center, Dr. Bhandari, Dr. Pancholi, Dr. Sharma, Professor Mehta used to come, and he's a regular visitor at this age. And we have also Professor Shivraj, member UGC. So welcome you all, sir. And Avinash, sir,
Avinash, I'm very fortunate that I knew all the directors, including the founder director. When I was at IIT Kanpur, then Mehta Saab was asked to do. I know Rai very well. I know Kanti is a very good friend of mine. And now you. So I'm very fortunate. I knew all the directors personally very, very well.
thank you, sir.
And well done, all of you.
Dr. Ghosh, please.
Yeah, thank you, sir. Thank you, Professor Chauhan, for your enlightening and inspirational address. Really touched our hearts, sir. Thank you very much. And especially you brought the issue of developing the indigenous infrastructure and to run these research facilities efficiently in India. And at the end, sir, you have conveyed the concept of enjoying your work, which is, I think, is very, very important. So thank you, sir, for your encouraging remarks. This will be our motivation to excel in future. Thank you very much. So now I would like to request Mrs. Anuradha ma'am, distinguished scientist, Indian Space Research Organization, Bengaluru, to deliver the keynote address. But before that, it is my privilege to tell you very briefly about her scientific activities and achievements. Mrs. T.K. Anuradha obtained her degree in electronics and joined Indian Space Research Organization in 1982. Her field of expertise are analog, digital, and power electronic systems. She also got extensive experience in the field of embedded system, automation, and system engineering. She was the leader of the team for the successful realization and launch of GSAT-9, GSAT-10, GSAT-12, GSAT-17, and GSAT-18. She was appointed as the first woman project director from ISRO Satellite Center for GSAT-18. As a recognition of her successful career and immense contribution towards the satellite-based space research, she had received many awards and appreciation. Among them, I would like to mention only about a few. She had received Women Achiever Award in Aerospace and ISRO Performance Excellence Award in 2019. She was honored by the honorary doctorate degree in 2018. She got ISRO Merit Award for the realization of indigenous communication of the spacecrafts and also ISRO Team Award of GSAT-12 2012. At different times of her career, she had been honored by Women Achiever Award, Women of Distinction Award, Jewel of Karnataka by many organizations and institutions. She rose up to the level of distinguished scientist in ISRO and had been superannuated from that position in 2020. So with this brief introduction, I would like to invite Mrs. Anuradha ma'am to deliver the keynote address. At the end of her address, she will be available to take up a few questions. Kindly type your questions and she will answer those at the end of her presentation. Ma'am, you may please start your presentation. Thank you.
Thank you, Dr. Ghosh, for the kind words. Respected Professor A.C. Pandey, who has been very kind to include me in this wonderful event, and listening to his lecture filled my heart with pride, what India can do and what kind of infrastructure we can have here. Thank you very much, sir. And listening to Chief Guest Professor Chauhan was really, it was so exhilarating, and I'm sure it is so motivating to all of you who have been participating today. And at the outset, my hearty congratulations to all of you on the Foundation Day today. So today I would like to take you through a similar proud journey of Indian space program, while as we discussed with Dr. Ghosh, who has been very kind to guide me through the last few weeks how to go through this event. We had several topics in mind what we can address, and we concluded that we'll touch upon everything, and there is shortage of time, and I'll try to do justice. So I'll take you through that. I know it's a field which you're not working on, and it is so great that I am with all you elite professors and researchers and wonderful students here. You're doing great things, but it's not your field. But it's always interesting to know other fields. Today, it was so exciting for me to know about your infrastructure, and I'm sure I can instill the same excitement in all of you about the space program of India too. So, first of all, I hope it moves. Yes, I know how to move the slide now here. So I would like to just give a very brief of what is space. When we are talking about space, we all know from all our cultures, wherever you are from, we all believe the old cultures that we are made of the Panchabhutas, or the five elements: the earth, water, fire, wind, and the space. And we call as Akash in India. So this Akash is all encompassing space for us. And people started with a fear of each element, humankind, when they started. And the fear brought in the worshipping, worshipping so that they get the blessings of these very tremendous and mighty elements. And of course, the human beings are always curious by nature, and nothing can stop them. They need to understand what it is. The knowledge gained, it helped them to harness each of these elements too. In the process, I think the space was the last. Marvelous space, it is so fantastic. It is unbelievable number, so vast, and it is estimated at least 200 billion galaxies are there in the observable universe. I'm using the word observable because the universe is eternally expanding, and it's not a lack of instrumentation that we are not able to see the entire universe, because the physical process is that it is so vastly and at a great speed it is expanding. So by the time it reaches, we are sure that we haven't seen other things. So observable universe is limited compared to the entire universe, and each galaxy has millions and millions of stars. And if you just see the observable universe itself, it is 93 billion light years in diameter. I mean, it is all, which is way beyond anybody's imagination, and many, many wonderful phenomena are going. So are we talking about that space? When I'm talking about our space program, so I would like to technically define the space as something which is above 100 kilometers from the surface of the earth. That is where the aerodynamic principles cannot work, like you can move an aircraft or something like that. So that is a technical definition. We call it as a Karman line. Scientists who studied these phenomena about the atmosphere, and that is defined as the space. So when I'm talking, I'm referring to the space here. So the space looks, as I told, so beautiful, shiny stars, everything, but it is a most hostile environment you can come across, with all kinds of, possible distractions that can happen to the human beings or life, or to the instruments you can put in the space, as I defined, the solar flares or the magnetic storms. The phenomena are enormous, the cosmic radiations, and though the Van Allen belts are helping us by trapping those kind of charged particles bombarding us, but for the spacecraft, passing through those entrapped charges is a great challenge. And hard vacuum, and the temperatures are extreme because of the vacuum. and the gravity drags by the bodies. It is innumerable problems. So when you really see it's a beast, space is a beast, and how to conquer that. So when it is so arduous and naturally so expensive to reach this area, why was there a quest for space? So if you see, the scientific and adventurous nature of the human being is one thing which took us there, definitely. The curiosity, of course, for centuries together, people have been studying about the space, observing. Even in India, we had wonderful recording of the constellations, the movement of the bodies, heavenly bodies. And this kind of knowledge and exploration was a one window when you look at it. The other one very soon opened was the other window of the possible applications and the business potential, the revenue it can bring. And further, today it has also become an essential frontier for the survival of the nations today. So it all began long back, World War II, when it was ending. We had the astronomical knowledge, as I told, with the great minds who had been doing for centuries together. And at the same time, it was a V2 rocket which was brought in during the World War II, which bombarded UK and other countries. And the space technology, I must say, started with that V2 rocket. The post-World War II scenario, the man behind this rocket, von Braun, he became the property of United States of America, and his assets became the property of the then USSR. And both of them had this great advantage to reach the space, and then started the space competition between the two countries. And obviously, a lot of advantages were seen. Apart from the exploration, as I told, you can put instruments and you have a large view. You can see entire globe, 1/3 of the globe you can see when you put at a 36,000 kilometers. And you can provide whatever happens on the ground, calamities, you can give, not worrying about your sentinels are working in the sky, and they can provide the service. And uniformity in the surface, whether you're in village corner or you're in the city, anywhere, whether it is populated, not populated, you could get the uniform service. And such wonderful thing. And even for the scientists, the lack of atmosphere was a great boon to observe the sky. Put a telescope in the space and then try to see wonderful universe and understand it. And long periods of time you could work without any maintenance, etc. And then, the history started. There was Sputnik in 1957, and there was no looking back. You can see, I'm not going to read all this. And humankind went beyond the Earth and its influence to nearby planets, and of course our own moon, and much beyond. And we even started touching beyond the solar system. That is the kind of the technology that got improved, and wonderful. And I must say that we are very proud. India is amongst the handful of the spacefaring nations today. But our aims were different. I'll cover that. So what was the space dream of India? So it was, as I told, 1957 was the first satellite which went up. And where were we? We were with the unhealed wounds of partition, the newly liberated, newly acquired freedom to the country after centuries of, under the governance of other countries. And still integration of many states was not complete. And we had wars with the friendly neighbors, and economy was in doldrums. Food was a big problem in those times, and we even had to import the food. And yet today, if you see, India has emerged as one of the fast growing economies, and it has done laudable progress in every field. There was white revolution, green revolution, and the sustenance. It was a great wonder it went in. And today, modern India is even ready to ask for a permanent seat in UN, is one thing. So those were the days. 1957, first satellite has gone. And where was India, as I told in the background? And there was a visionary, Vikram Sarabhai, who thought that we have to go ahead with the space program. Why? Not to compete with anybody, not to compete with any giants, but we have to bring those advanced technology for the betterment of India. for the betterment of the young India, which was free and which was having great dreams. So that was a kind of conviction where he brought in this kind of concept. Look at this. Who will accept a strategy when we are worrying about the food and we're worrying about the day-to-day activities? And can anyone say that I want a huge investment for the space program and for the scientific primary goal? It was not affordable. It was impossible. People would only raise their eyebrows and laugh at you. But you think of an agenda which is much more meaningful. Investment in the development of the capabilities so that we can bring those applications to the society. We can bring the betterment to the society. And in the process of bringing those capabilities, whatever infrastructure we are developing, we will use it for the further research. We will do it step by step. So that was a wonderful way, very innovative way the space program was born in India. So if you look at that, I don't want to bore you with the history, but it is something, it is your inheritance, youngsters who are here. It is your inheritance and you have to carry it on, not necessarily in the space field, in any field. That is a kind of bravery and boldness Indian scientists had, Indian visionaries had, and they will continue to have too. So 1962, Indian space program started as it was started as a committee, Indian Committee for the Space Research under the aegis of Department of Atomic Energy, which was already a department. But since then, there was no looking back. Very soon, we were, so good in international cooperation that we could bring in the Tumba launch center where the sounding rockets could be sent. And we had our own sounding rocket by 1967. In fact, it was dedicated by UN for all the nations for the sounding rockets. That was the wonder. When there were two giants fighting for the space dominance, we could bring those giants together to cooperate and bring in these kind of activities in India. That was a great thing. And as per the vision, it was always an application first, what we can bring to the humankind first, rather than showing off or establishing something. No, that was not the idea. So even using the foreign satellites way back in 1960s, we brought in, one Earth station, how to bring in simple programs like satellite instructional TV, which was used by ATS-6 of USA. And then we also brought in the telecom experiment STEP using the French and German satellite, bringing that. So it was a great thing that people got convinced. Yes, see, it is very important. We need to convince the government because it's a public funding. So the applications have to be brought in, which were very successfully brought in. And very soon we had our own Aryabhatta satellite in 1975 and further many experiments with Bhaskara and Apple. It was a wonderful journey and there was no looking back. Today, ISRO sets India on the world map of spacefaring nations. You can just count on hands number of people. When we say spacefaring, today every nation is space technology using. But how many are spacefaring? We have our own operational launchers and we have our own building of the satellites. We can launch, we can provide services, and we are very few. There are very few countries, and India is one among that. And this is our heritage. So the applications, as I told, was always important for us. So applications, very clearly defined programs were set by Indian Space Program, remote sensing, communication, meteorology, and navigation, and huge number of applications, a plethora of applications by clubbing. They were not separate identities. Using together, so many applications came up for the betterment of the society. I'll just briefly mention those things to you. So how ISRO grew is just a simple map I wanted to show you. Whether very defined programs, Indian launches, they went with the workhorses. Today, you know how it has grown. Today, our Polar Satellite Launch Vehicle, which was meant for low Earth orbit satellites to be put into the orbit, it has taken satellites to the geosynchronous orbit. It has taken a satellite to the moon, it has taken a satellite to the Mars, and it made the world history, taking 104 satellites, and the highest number of satellites at that time, later on, which was broken recently by SpaceX. And communication, we started with a simple Apple program, and today we are there at high throughput satellites, which are state-of-the-art satellites. Remote sensing satellites, which we started with a simple experiment with Rohini and these kind of small satellites. Today we have satellites which are dancing in the sky with great capabilities. Navigation was later joined, and of course, remote sensing included meteorology and weather monitoring too. So though it developed as another important field, we consider it as part of the remote sensing itself, remotely sensing the weather conditions. And navigation, today we have our own unique constellation. I can touch upon it. And notwithstanding all that, just like the vision, after having brought these to the society, we started using those capabilities for further space research too in the explorations. That is a way in each of these things, in each of these defined programs, the visionary programs, the way they were put, was fantastic. Each one starting for an application and then going ahead. So if you see the remote sensing, I think I already told you, today we have hyperspectral imaging. Remote sensing means you have to sense the radiations which come from the earth and from various objects. So how well you can grade those spectrum and the sense it is hyperspectral. And all weather imaging, whatever is the weather condition, day or night, we can get the images today, and we can get sub-meter resolutions today. So it is just one small thing I want to show you, how from kilometers of resolution, we have gone to sub-meter resolution, how the same area started looking. You can have a look at it. So this is the way India has progressed in remote sensing. And in early 2000, first decade of this century, we were the best in the remote sensing for these societal applications today. So that was the way it was there. SATCOM 2 ISRO missions went on with simple satellites, and there was something innovative about these communication satellites. It was like, we did not have so much of budget that we can keep on putting for each application, one for broadcast, one for telecommunication, or one for weather monitoring. It was not possible. So India brought in, the ISRO brought in fantastic, mix and match of payloads in the satellites. That was something very, very innovative. It was first time anybody had tried it out. We had a part of the payload which was for disaster monitoring, part of the payload on the same satellite which is doing the communication, which was apt for that time, which was sufficient for that time. We didn't want to do something so big and being wasted. How compactly we can pack everything together. From humble roots, today we have gone to state-of-the-art satellites and a lot of indigenization. So many technology like complex antenna systems and rotational system, advanced power systems, and advanced RF systems are all indigenized today. So another great story was the IRNSS, Indian Regional Navigation Satellite System, which Honorable Prime Minister named as NAVIC when the 7th satellite constellation was completed, navigation with Indian constellation, NAVIC. A beautiful name was given to that. It was an innovative solution. Why do we need to have, navigation satellites? If, we have GPS, everybody has GPS on phone, you can use it. But every spacefaring nation today has understood being, independent, having an independent system of its own. We have seen in India where when some critical operations were happening, strategic operations, the GPS signals have been deterred. So, it is essential that we have our own navigation system. At the same time, we cannot copy same thing what GPS or GLONASS did with, 20, 30 satellites going around the earth, and which is very expensive to make, maintain, and complicated. Whereas our application is for India and around. So 1,500 kilometers around India, we have a beautiful navigation system, mainly meant for strategic application, and slowly it is coming to the commercial applications too today. That was some unique way of bringing regional navigation system, which we are very proud. In addition, we also brought in with our own communication satellites, picking back the GPS signals and having our own, standard stations all over India and correcting those signals and getting very precise. We called it as Gagan system, that is GPS aided geo augmented navigation. So in navigation, two ways of systems came out, and today Gagan is part of all our aircrafts, and which are using it for cruise, how they are doing it, direction telling. So we did all these things, but did we meet the vision? Was it becoming realized or not? So how did it apply to the real life problems? I would like to touch upon that too. So what is life? What is the quality of life that we can have? If we can help them with regard to sufficiency in the food, environment, health, education, which are most essential, and security of the country, and managing the natural disasters, and can we bring in growth in economy in terms of business, commerce, and growth of industry with technology, etc., and of course entertainment too. This is the quality of life. Have we done enough? I would like to show you a bit of it. So if you just see, these satellites are, they are the eyes in the sky. So today, there is no department which is not using the satellite applications, whether it is for agriculture or anything. I don't want to read out the list. It's almost every important department which matters to common life. And the applications obviously are agriculture, forestry, water resources. All these departments are using, whether it is, identification of water bodies in, it happened for 168 districts as a program, and later on it is being used as a continuous application, whether it is potential fishing zone for the oceanography, and whether it is weather monitoring and disaster warning and management, whether it is decentralization, which is the dream of India, Panchayat Raj, because we have more than so many lakhs of villages, and we need to decentralize, and every village, the Gram Panchayat can operate on its own. Lakhs of panchayats have been provided with very accurate asset monitoring and town planning and digital elevation models, river joining, and innumerable applications you can think of as you go. I'm getting a message to approve something. Okay. So now after I said yes, I'm not able to go ahead. Sorry. Can someone help me? So it has gone into a pen mode.
Yeah, usually at the bottom of the screen, if you click it, then there is some highlighter, all sorts of things are coming. So probably you have to deselect it.
Achha.
Since it is Mac also, so I am not very conversant in the Mac. Or you cannot do the slide change, right? You cannot change the slide, right?
Yeah, I'm not able to change the slide. Decline.
You can use the scroll button, which is there.
Yeah, I was using that actually. That's what I always say. It is easier
And
to
you can
make.
share, unshare, and then again share.
Yes,
Yeah.
this is also another option. You just unshare and come back with the PPT. Yeah.
Okay. It's kind of okay. So stop sharing. Then I'll share again. Brilliant idea. So we go there. So I was telling you about this, and of course, if you see the communication technology, world has really become flat with whatever has been, at least India has become flat with our geographic topology, whatever is there. We can connect anywhere today, whether, India is one country with a very complex demography, and the number of TV channels, the DTH channels, the number of VSATs which has been said. Today's business today, whether you're operating, your stock exchanges or exchange of the scientific instrument from Leh, Ladakh to the Bangalore center, anywhere, it is possible through the satellite links today and the kind of video conferences we are having. And your colleague need not have to be in India today. It can be anywhere else. There is no day or night. These kind of things have been made possible, and Indian space program has provided for the Indian users all these facilities with the most successful way. And communication at any point, whether you're in the sky or in ocean, it is always available today. So it's a big thing. Like there is nothing like I'm traveling, how do I contact home? There is not possible. No such thing today. Through the satellite links you can do that. And variety of societal aids, search and rescue with one simple button. Whoever is lost over the sea, or a fisherman or a mountaineer, one button and the information goes to the satellite, and immediately it comes to the control centers. And with a combination of the location finding with the navigation and the remote sensing data, they can definitely help these people. And tele-education, telemedicine, they were wonderful programs which are gone. And in fact, when I was director of SATCOM, with all the land, today what we have cellular usage, we were wondering whether we should continue with telemedicine and tele-education, whether we can stop and use the bandwidth for something else. So we had an interaction with all the state secretaries, and we found out that it was most cherished and most used for the corners where you may not get the cellular ranges, but the satellite for the hilly areas, wherever remote area. Beautiful programs are running all over the country, and they didn't want us to stop. And especially defense, they had the telemedicine facilities at the very remote areas, in the hilly areas of and mountainous areas of Himalayas, where they were extensively using the telemedicine. And it was really gratifying to know that these applications are so well sought after. And just as we were listening about Atmanirbhar India and government program of Digital India program, and very recently we have included our high throughput communication satellites today, nearly along with the optical fiber cables, of course, which go to most of the places where it can reach. And satellites are reaching to 6,500 unreachable gram panchayats. And from each gram panchayat, so many, 20, 30 villages or 50 villages under the gram panchayat, all are getting connected, which is another big story which went beautifully. And navigation, I don't have to spend time at all. All of you know very well how we are using, but you may not know certain very peculiar applications of navigation. Of course, you all know on ocean or sky aircrafts and all that you can use, but you also use it for very precise timing, because of it also gives the coordinates and the time, precision time, from using atomic clocks on board navigation satellites. It is used for power grid synchronization, and even for disaster monitoring, etc. It is extremely important to find a border when there is a forest fire, which is extremely useful for this. These are all innumerable kind of applications with the navigation, clubbed with communication and with remote sensing. It is going on. And of course, the fourth frontier of any nation today is defense, and every component of defense, whether it is a control, communication, computation, surveillance, reconnaissance, intelligence, or command, all these systems are extensively being used, whether it is navigation, meteorology, or remote sensing or communication. They are totally used in that sector too. And disaster management system. One is disaster detection, when you can detect well in advance some cyclone hitting or what is the environmental condition happening, and you can protect the lives of human beings and the cattle. And of course, you may not be able to protect the property, you cannot do anything about it. At least you can move the people well in advance. Today, you hardly find people who are dying because of this kind of catastrophe. But that is one aspect of it. If you see the other aspect, the management of it, when there is a catastrophe, the government needs that it has to bring out solutions. For the solutions, this kind of management, what is there, the satellite data is extensively used. So it is a feedback system of mapping and event detection and how to bring in the reliefs and how to concisely, quickly do this. It is a big program that goes on. And we talked about the common people. Common people in India are mostly the villages. How did we help them? So the beautiful concept that came was the Village Resource Center. They all over India, all the states and the union territories brought in the Village Resource Center concept, which was introduced. And in these centers, we brought in all these applications, what I told, whether it is agricultural or fisheries or tele-education, telemedicine, all these things, by putting one receiving station on some important building in the Gram Panchayat, whether it is Panchayat office or a school which is there, you bring it in, and a lot of information was passed on specific to the areas. There were fishermen for whom the data was given, where to go for the potential fishing, and weather conditions, weather monitoring, not to go, alerts, and this kind of information was one hand. On the other hand, educating the villagers about what is happening. And on the other hand, again, helping the administration that you have a direct contact with the Gram Panchayats and you can bring in the administration in a more focused manner. So these were the Village Resource Center experiments, were a great innovative application which was brought into India. So having seen these applications which has affected in day-to-day life, how it has improved us, whether I'm in Timbuktu or wherever, I can, access my money from my bank, or in the remotest village, people can access the specialized hospitals, and whether it is education which can be brought through these means, is all grassroots level, it has been done, true. Then how did we use these technology to go further into the space-based research? So what are the tools which were brought in for that? You already know. So our first step beyond Earth's influence was Chandrayaan-1. Yes, it was such a success. Using our simple PSLV rocket, we took a small satellite with, again, we are experts in putting the payloads which are absolutely essential in small satellite and carrying it. And it was such a success. That was a satellite which also stood for international cooperation. And we had a moon impact probe with the Indian flag on it, which fell on on the moon crater. It found traces of water. That was the first truth that came out, that the first reality that brought out that there are traces of water. And it was a great experience for us how to carry out mission beyond the Earth's influence. So it taught us a lot to go further. And we had Mars. Mars, again, we used same PSLV. We went with our own route. It was a great lesson to go beyond Earth and Earth system, and where a lot of automation was learned. And these are essential for further space explorations, of course. Beautiful Mars photographs came, and I think today you might have read in the paper too, not with the Indian satellite. Of course, we didn't have a payload for it, and they found in one of the craters of Mars too, there is water. So these kind of things are never ending. And of course, we had the next visit to moon, where we wanted to dare to land on the moon, and unfortunately with some very simple problem, but which, it went ahead. We lost the lander, but building the lander, testing it, and going through it is a great lesson for us. In fact, failures always teach us better than successes. And That was another experiment. And another thing, probably you people might have heard, scientist community, that observatory in the sky, AstroSat, which has the entire range of the X-rays and the UV for studying the phenomenon. And this small satellite, which went on PSLV again, is much sought after all over the world with the the physicists who are looking into the phenomenon in the sky. And this satellite could detect 9.3 billion years ago a galaxy formation. It could bring out a beautiful picture of it, and scientists are analyzing the data, and a lot of gamma ray bursts and many phenomena have been identified by this satellite. This was one other beautiful experiment in our own way with our limited budget, what we could do, and which is so well received all over the world, in fact. And we have another beautiful thing coming up, that is the Aditya program. Aditya in Sanskrit means sun, the sun study. So while you have read recently about the Parker probe, which is very near to the sun, we have our own experiment which is coming up in a year or two. We plan to put it in a place called Lagrange point. It is a two-body problem where there are certain stable points between two heavenly bodies. We are going to place the Aditya satellite there and create our own eclipse and study the sun. So though we are in solar system and we have done so many advancement, hardly we have understood sun's corona. So this is going to be another satellite which is going to help us to understand better. And we are going one more step ahead, joining the league by putting human beings into the space. And this is going on, and it's not something that happened over a couple of years or something. So as I told, while we were meeting our bread and butter, the main activity of bringing applications to the society, with the technology, experiments have been going on. We had been developing the space suit, and we had been developing the chutes, and we did the space capsule recovery experiment for the material which is required to re-enter the Earth, how it can withstand. And we had this Padabot test, and these are all essential things which are going on. And we also had the crew module re-entry test which was done, and we have done our own humanoid called Vyoma Mitra, which will go in one of the first flights for the Gaganyaan, so that we understand before we really put a human being, we understand the entire thing. This program is also going on in a great way. So what was it that made ISRO? ISRO is a high learning organization, I'm sure, like IUAC too. So what made ISRO a high learning organization while it is serving the common man is something, is a thing which people keep looking at. And already Professor Chauhan has beautifully told that it is a determination first and foremost, and hard work. So if you see these iconic pictures everywhere, whoever from ISRO, they will show you these pictures. These iconic pictures are a symbol of the dedication of the people who, the people who you are seeing on the cycle or near the bullock cart. I assure you, they were the eminent scientists who were working on those days, who were there. And I also had a picture, I could not put it here, where you can see Kalam sitting and working on one of the things on the floor. It was a beautiful picture. So these are the kind of people who motivated and who brought in that kind of culture, infused the culture that, I'm also proud to say that when I started my career, I was a test engineer, satellite test engineer. We had to interface to the satellite, and our interfaces would go into the tunnels. And I never hesitated 1 minute also to enter into the tunnels, solve the issues. And we'll never wait that somebody has to come. We think it is our house. If some dirt has fallen on the floor in my house, I don't wait till tomorrow morning for my mate to come, I clean it. So our work, our office, our organization was always our home. That is a kind of culture we have always got into it. And it's, as Professor Chauhan told, it's a passion for us. So, we enjoyed doing every bit of it. the failures, the successes, and knowing some user comes and tells you that he used it, it gives such a great feeling, I cannot tell. And we don't lose easily. We have a lot of grit, and this is a continuous learning. The scheme also is such that it doesn't become any other industry. So to get a promotion, it's like doing your engineering again. So there's a panel of experts and from outside too, not necessarily from ISRO, and you need to know everything from your first year BE to whatever is happening under the sky. So you have to be on your toes, learning all the time. And there is a lot of respect, whether he is a wireman or a tradesman, he comes with a new idea. There is a lot of respect for his idea. He becomes the leader for that particular event. And that is a kind of ownership ISRO gives to each and everyone, whoever he is or she is. And it is I would say it's a religion which goes in ISRO of commitment. And it's important. It was made very clear that we have to gain the confidence of public. We cannot just talk on air, but we have to make sure that public feels and experiences what are the benefits which are brought by ISRO. So that is a culture, and which is always shaping the strategies for us. And these strategies are also defining the destiny for ISRO. So innovations are part and parcel, and we cannot survive otherwise. And I already told you about navigation system, which is a beautiful innovation that we have for regional, and we are satisfied with the requirements fulfilled. And we had satellites made with combination of payloads, which are unique to India, but it serves us. And having is, workhorse PSLV and taking it everywhere by defining and putting, your efforts in a mission and how to take it there and how to optimize. These things have, are some of the examples. At the same time, the most important thing has been the inclusiveness. So whatever I'm telling, please don't think ISRO has done it by itself. ISRO has always been inclusive. All the departments, we made sure, even at the beginning of the birth of the space program, that there is a planning commission committee with all the connected departments together who understand what we are giving and who tell us what is required. And because they are the implementing agencies, and if the link fails, it does not reach the grassroots level. So it has been that inclusiveness with the government departments, with the universities, academia, and many research institutes, public sectors, and international cooperation. So the whole thing today, like, I felt very proud listening to the infrastructure of IUAC. So this is a wonderful world-class infrastructure which has been brought in by ISRO too, for building the satellites, launching, and the Earth stations, and getting the services. Huge, there is a huge base of industry which has been developed. And industries, in fact, today, if you take a rocket, 70% is done by the industry, 30% only is done in-house. So that is the way they have been, trained to do it. And satellite components, satellite fabrications, they are successfully able to do. So it is a win-win situation. Overall, this has helped to provide the national progress. And it's always that another factor in ISRO is, equanimity, and we don't get bogged down by failures. So every time we are burned down to ashes, we come back as phoenix. And because of the strong reviews and analysis that go on, even when Chandrayaan-2 lander did not work, we did not go home and rest. We were there all night, but the moment it happened, the next day there was a room with the committee, and the next room set up as a lab and simulations. Continuously it went on to understand what it is, and introspections where we go around. That teaches us a lot, and we fly back always. So that is ISRO. So we are very proud of ISRO, and there was always 2 rupee note with Aryabhatta on it. Today our value has increased, and it is Mangalyaan, which is shown on 2,000 rupee notes, right? It's always near to your hearts. Thank you very much for your kind attention. So I can take some questions.
Thank you, ma'am, for your excellent presentation, I would say. And during the last 45 minutes or so, you have taken us through a beautiful journey of space. And we came to know the history of Indian initiative in the space program, the details of the satellite, and the huge societal application, which is having a direct impact on the Atmanirbhar Bharat. So, ma'am, I'm sure that all of us have enjoyed your presentation very thoroughly. Thank you very much.
I enjoyed it too. Thank you.
So, if you allow, then there are few questions in the chat box. So, can we just take a few questions?
Yeah, could someone read out the
Yeah,
question?
I'm going to read it out for you. So Chirag Sharma had asked that, ma'am, after Neil Armstrong and Edward Aldrin, when space agencies like NASA, SpaceX, and ISRO can be able to send a person at moon. So when this, let's say the different space research centers in the world, they will be able to send a person in moon.
Yeah, already, there have been several men and women who have been in space and on the moon also. Some, I think, 18 people have gone, but I think 12 people have landed on the moon. And one ISRO will join to it. ISRO has, as I told, we have started our initiative. So there are certain things. Today, ISRO is in a state that we can have a equal dialogue with the other spacefaring nations. So I'm sure it's going to happen, because today we have also launched so many foreign satellites, nearly 350 satellites we have launched, and while we take our bigger satellites outside, so there is a give and take. So when we are at that level, I'm sure it will happen. And international cooperations are not new to ISRO. And today, whether it is NASA or ESA or any other space agency, they have the confidence in India to take our cooperation too. And many such dialogues keep happening. And today, even for our human space program, we are having the cooperation from Russia, we are having cooperation from France, it is going on. So in the same way, we are also contributing to their programs with respect to sensors or instruments, it is going on. And if you remember, one of those such international cooperation where Rakesh Sharma went on to space too, so I'm sure it will happen, but I cannot tell you which year.
Mm-hmm. Okay, and there is another question from Akanksha, and she is probably not very happy why the space and astronomy is not in the school curriculum. So her question is that, do we see astronomy getting into the school curriculum? Astronomy.
Actually, yeah. See, when you say astronomy, you all know very clearly physics is the basic thing, right? So you need to have a basic science degree to go beyond, right? So it is more of a specialization. Like, for example, if you say why there is no course on surgery, it's very difficult. It is a specialized thing, right? So you need to have a basic education level. Then you can choose, and a lot of people are doing. And in Bangalore, we have Indian Institute of Astrophysics too, and I'm sure there are other institutions elsewhere too. And people are pursuing in premier institutes. But as she rightly told, it is not so widely provided course everywhere, and that's the reason. We always enjoy talking to students from ISRO. We go and tell them what is there, because they have to get induced into these streams, not the regular streams which are always going on. Of course, all streams are important. These niche streams, we need more students to come up. So more students come, more universities will offer automatically, right? And ISRO also has got its own institute where it is taking up on space technologies and all that. But if you're talking about the astrophysics, that is purely scientific in nature, there are institutes, but it needs a basic degree and interest for people to pursue.
Okay, and the next question is...
Dr. Ghosh, I will add one thing here, because CBSE has added one module for 11th class, in which in astronomy, what are the Indian traditions and practices? So they have enlisted all those activities, And at least from the perspective of making people aware, the students, this is going to get included in the school curriculum, in which they will get a good idea and they will get motivated to take discipline for further studies. So that effort is also being made. Yes.
Beautiful, beautiful.
Dr. Ghosh, can I ask a question?
Yeah, please, please, please. Please,
So,
sir.
I just wonder if you put in perspective for the recent rush in the space travel, be Middle Eastern countries, especially UAE and Saudi Arabia and others, getting hugely interested and getting together with countries like which are pretty so solid in space research, China. So while India is success in space is unquestioned and capabilities are realized world over, you see the increased competition to enter into space, as it were, both for business, for commercial purposes, as for science, is going to become much, much more intense. And if yes, then I mean, India has done very well, so I don't think that needs to be repeated. But now, since the competition, especially money, is coming from Middle Eastern countries, how do you put that into perspective for the younger kids?
True. One is the excitement of the space itself, which is being cashed on the commercial purposes, as you rightly told, taking to the Karman line point and then showing the space and then coming back. That kind of human space programs, I mean, I personally think is more of a gimmick, and probably it has an advantage to infuse the interest in the common man about the scientific aspirations. But when I look into it, there is the human in space. We are not taking it as a competition, sir. Definitely not. Because why we have to send humans is one thing, one we all need to understand. Because most of it can be done with artificial intelligence and robotics. But if we are going into a further deep space programs, the instantaneous decisions humans can do better is one aspect of it. And other thing we have a lookout is India should be equipped that whenever there is such a chance that a habitation is possible outside, we should be geared up for it. So like any other technology, these technologies also will not be easily be shared with everybody, and there are a lot of complexities in that when the human life is concerned, and we have to learn by ourselves. That is our motive to go ahead rather than any competition. And of course, any, like as I told, we can have the humanoids which can do these activities, but what is the capability of the human being and sustaining in the space environment, that is something out of curiosity and scientific aspiration. That is all what we have in mind rather than any competition, sir.
Okay, unfortunately, there was some break in the meeting. It went out and again we had to come back. There is some technical issues. We don't understand why this has happened. Maybe some kind of a hacking or whatever. So the next question is from Vedant. Ma'am, why there is no private space agency in India like SpaceX?
Yeah, actually, Vedant, if you're following up the latest news, for the last couple of years, there has been a very strong move to bring in the private industry. Of course, private industry has been supporting ISRO for everything. As I told, 70% of the system for rockets are made by private industry. But is SpaceX, we want them to come up. We don't want them to be just the suppliers to us. New policies have come up. Probably you have been following up on that, and a lot of people have shown interest. Only thing is, we tried for the last 20 years the same thing, but it is a huge infrastructure investment, which is very difficult for any private company to start on its own. Somebody like Elon Musk, somebody who is so rich, has to come here. But today, government has opened up the ISRO infrastructure for any private company to utilize and then bring up their own business. fact, as I told, many of the business activities ISRO need not have to do, like DTH satellites or VSAT satellites and all. What will not be picked up by business and what are purely scientific explorations, we want to continue. We want to continue with the research. And this is exactly the thought, and in a very full force it has come. You might have read in papers also about the formation of InSpace and how anybody can approach InSpace and get the help from ISRO and do these things, which is happening. But why like SpaceX? SpaceX has its own history. If not like SpaceX, it can be any Indian private industry who are doing good, and I hope they will make use of the ISRO facilities, ISRO expertise, knowledge pool, and they go ahead with those activities. And that is the intention. New policies have come up.
Okay, ma'am, another question.
Thank you,
that
ma'am.
what are ISRO's thoughts on deep space exploration, such as like launching a space telescope similar to Hubble Space Telescope?
Yeah, I mean, that is something we all look forward to. In fact, in those efforts only, as I told, the Astrosat, a small satellite was put, because we also have constrained budgets, etc., and we have to do, and technology. In fact, Astrosat itself has instruments from various scientific premier institutes from India, TIFR and IUCA. These people also have worked on it and have put the instruments on that. So we can give a platform for whoever is interested. And building a telescope is something technologically very challenging, and we would like to do it. And moreover, I think they will go more as collaborative activities now onwards, like ESA does with 10 countries together. So we always, dream that like ESA will also have an Asian Space Agency with all our neighbors joining us, and funding, and we should be able to do that. Today, any technology is not a challenge, but funding is a big challenge. They are all very, very expensive, and there is nothing impossible for ISRO, and any technology we can achieve.
So, ma'am, few questions are coming that ISRO does have any student program like in +2?
Plenty of students. For example, there is, as I told, IIST, the Indian Institute of Space Technology, is there, where students are encouraged to study the space-related aerodynamics and space-related activities. That is one aspect of it. Otherwise, also we have many student programs from the premier institutes. And we also brought in some kind of mushroom laboratories all over India, wherein we bring in the facilities for the students to come and do their experiments. And there is a program which is running called Capacity Building Program, and that program is specifically addressing this. And this is something everywhere I give a talk, I'm surprised. It doesn't get popularized much, which is there everywhere. Probably we have to do much more publicity on these matters.
So, ma'am, there is another technical question. There are so many questions, probably it will be impossible to take all of them. So let us try to take most of them. So do we see India reaching that level of development that astronomical projects can be conducted independently, somewhat like Hisako Koyama back in times laid the foundation for a 400-year timeline of sunspot activity, which has aided researchers in studying solar cycles and magnetic fields?
Yeah, I mean, most generally people do, yeah, of course we can take it. We have a unit of space sciences, but most generally people get confused between astrophysics and space activities which are going on. So, but there is a very strong collaboration with such studies and ISRO. Obviously it is there. And we can take, but it is a question of, it's always how much funds we get and what we can do. And, so far, to tell you frankly, so far, ISRO has been all the time focusing on making sure on self-reliance. Okay, I'm not telling self-sufficiency, self-reliance in all the day-to-day activities, how to bring it. And today we are bringing in policies to hand it over and focus more on the research. I think it is bound to happen when the private people take up all these conventional satellites and what is required for the traditional activities when they take up, ISRO can concentrate better, because ISRO also has a certain number of people and certain number of funds, and which cannot cater for everything as of now.
Okay, ma'am, there is another maybe little interesting question. Ma'am, as ISRO has always been particular with space technology, are there any exploration program regarding finding new elements on asteroids around our planet or
Yes.
even the asteroids belt?
Yes, we have programs which are coming up, and there are a lot of today it is at a study phase and things are going on, and we do have on the exoplanets and asteroids and going beyond Mars. We have all those very enchanting programs are there, and they we don't publish, as I told, even human space program we have been working for the last 15-20 years. So when it comes to a certain stage, these will be announced, and there are programs.
Okay, and there are two questions on Chandrayaan. Chandrayaan 2, somebody is asking that why did Chandrayaan 2 lost the connection at the last? And the next question is that, is there any chance for the new and again startup of Chandrayaan 3?
Yeah, of course. Chandrayaan 2 repeat should have happened last year itself, but we had a serious problem with the pandemic and we had to close down, because we depend a lot on people from industry, and we had the epidemic outburst in many of our major centers, launch center, and we had to close down for months together. That is going to happen. Second, the first part of the question, why it lost the connection? Because there was a technical snag and it lost the control. The satellite, the lander which has to go, it has to go at, there is a gravity on moon too, though 1/6 of what is there on the earth, and there is a gravity, and you cannot crash land, but finally it crash landed. With all the analysis, you can see that it crash landed. So when that happened, the communication obviously we lost, because the instruments broke or lost or whatever. And the whole thing was related to the lot of algorithms are there, and everything is very difficult to test on Earth. It's a real time. You have to test in piecemeals and interface them together. And how 99.99% you can be good in space, but the 0.01%, if you're not correct, you fail in space. That is a risk we always have. And as you know, it has happened for all space agencies. In fact, ISRO was the first to reach Mars and orbit first time successfully. I'm not telling that that's a great thing. I mean, we should not fail, but it does happen. It was because of these kind of complexities. Everything that happens in space real time cannot be tested on Earth. And many things are left to simulations and our imaginations, the test cases, what we bring in, the limits we expect, these things can go awry. That's why we lost.
So, ma'am, maybe another last two questions we can take away. We are running out of time. So the one question is that are any future moon, Mars, or deep space exploration missions planned for ISRO? Another related question is that, is there any plan to ISRO for exploring Mars?
As I just now told, yes. As I told, we have moon missions, Mars missions, beyond Mars, exoplanets, on the asteroids. We have huge number of plans. And there is a plan to visit Venus too. And yeah, all these programs are there.
So maybe the last question that ISRO studying, because it keeps on coming, ISRO studying things like dark matter and dark energy, and are there any program to further continue our studies on these subject matters?
Presently, it is a highly research oriented, which physicists are everywhere. It's an enigma, the dark matter and dark energy. So when you try to see the universe and try to explain things, definitely there must be some matter which we are not able to feel, see, or sense it. That is the dark matter which is there, and the dark energy, because the way the universe is expanding, it cannot happen. I mean, something cannot go beyond the speed of light, but the expansions show that there is some other energy which is pushing it away, that is dark energy. So this kind of dark matter, dark energy analysis are always going on, but it is an enigma. We don't know when we can find anything about it.
Okay, ma'am. So probably we can stop here, and thank you very much for taking so many questions. So now we have come towards the end of the first part of our Foundation Day program, and this is the time of vote of thanks. Before that, I am having a few announcements. After the vote of thanks and national anthem is over, the special program for the student will start. So I request all the students and their teachers to remain connected in the Cisco link, and others may quit if they wish. After the national anthem, I request all IVC employees to assemble in the lounge area of our auditorium to observe the presentation ceremony for the employees who have completed 25 years of service, and that will be followed by lunch at the lawns in front of IVC's cafeteria. Now I'm having a pleasant duty to fulfill. So a warm and graceful morning to our honorable keynote speaker, Mrs. T.K. Anuradha, distinguished scientist, Indian Space Research Organization. Our honorable chief guest, Professor V.S. Chauhan, Padma Shri and former director, International Center for Genetic Engineering and Biotechnology, ICGEB. Respected Professor Avinash Chandra Pandey, Director, Inter-University Accelerator Center, our most valued invited guests, dignitaries, users of IUAC, school teachers, the beloved school students, and my colleagues and students of IUAC. It is my great privilege to propose a vote of thanks on this occasion of 32nd Foundation Day program of Inter-University Accelerator Center. Since our childhood, we used to observe sun, moon, stars, galaxies, and always used to be fascinated about the mysteries of the space and universe. Now we know that the satellites are one of the main devices by which we can explore the space efficiently. Today, this fascinating field of space exploration and this mystery has become more comprehensive and interesting through the vivid presentation of Mrs. Anuradha, and I am sure her talk will be extremely motivational for all of us. Especially for the students, her lucid explanation will definitely enhance their enthusiasm to explore the possibility to become a space scientist in near future. So we are indebted to you, ma'am, for your excellent presentation. On behalf of our director, on behalf of the organizing committee, and the entire fraternity of our institute, and on my own behalf, I would like to convey our deep sense of appreciation for your excellent presentation on vision to missions of Indian space program. We are indeed thankful to you, ma'am, for your gracious presence during the entire program. Thank you very much. We are also privileged to have today Professor V.S. Chauhan as the chief guest during our 32nd Foundation Day program. His kind association with our institute is very long and it is being continued since last few decades. Recently, we have been honored to have him as the chairman of our governing board of IUAC. On this auspicious occasion, on behalf of our director, Professor Pandey, and on behalf of all the employees of IUAC, I'd like to express my warm and sincere thanks to Professor Chauhan for presiding over the program and delivering his stimulating and encouraging presidential remarks. We are grateful to you, sir, for accepting our invitation and for spending your valuable time to spare your thoughts. My heartfelt sincere thanks goes to our director, Professor Avinash Chandra Pandey, for his constant support and follow-up. His encouragement, meticulous planning, and quick action were the major motivating factor for all of us. Thank you very much, sir, for your extensive help and support. I must mention our deep sense of gratitude for the gracious presence of all the dignitaries. You always stand by us, you always guide us, lead us, and inspire us. Your presence makes us feel proud. We are thankful to you for your active participation. After the present program will be over, another program related to the virtual tour of IUAC and the demonstration of a few experiments will be webcasted through the interactive session with the students and their teachers. The complete recording and the editing of the program, what we are going to see after a short while, was performed by the efficient professional of Consortium for Educational Communication, known as CEC. On behalf of IUAC, I like to express my deepest gratitude and thank to Professor J.B. Nadda and Dr. Shunil Mehru, the Director and the Deputy Director of CEC respectively, for their kind arrangement to prepare the video photography. We have been fortunate enough to be backed by a team of motivated and dedicated group of personnel of IUAC who know their jobs and are excellent at execution well in time. I like to express my gratitude and thank all the members of the organizing committee, the entire team of administration, and the other employees associated with the function for their enormous effort and cooperation to make this event a success. The involvement of the school students is one of the major objectives of our Foundation Day program. This year, we are fortunate to have more than 300 students from various schools of Delhi and other states who have registered to participate in the program. I hope that all of you have enjoyed and will carry a cherished memory of our program. Thank you for your interest and enthusiasm to participate during the program of our annual day. The teachers are the role model to the young generations, and they are also our inspiration. We feel honored to have the kind presence of so many teachers with us during our Foundation Day. I'd like to express my sincere thanks to all of you, ma'am and sirs, to participate in our program along with your students. Last but not the least, a sincere thank from my heart to each one of you who made this annual day celebration memorable for all of us. We thank you all for being with us. Have a great day and have a great week ahead. Thank you very much. So now we play the national anthem, and may I request everybody to please stand up during the national anthem and please adjust your camera in your laptop, phone, etc. But before doing that, I would like to request Professor Pandey if he wants to say something.
No, we can go for last time. Yes.
Okay, sir. So now a national anthem. So we should stand up.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Okay, thank you very much, ma'am. Thank you, everybody. So students and teachers, please be connected.
So, sir, are we going to go to lounge area? I mean, auditorium, lounge area now.
Yes, so there will be two programs. So we'll be going to the lounge area for the 25-year service recognition award ceremony, and the students and teachers will be watching the video, and they will start interacting with us for any questions and other things. Okay.
Sure. Okay, sir.
Actually, those who are guiding through virtual tour, they should stay back.
Yes.
And the recipients and also all the well-wishers who don't have any other responsibility in this virtual tour, they can join there.
Yes.
So this activity should not get disrupted,
No.
right?
Yes, sir.
Okay.
So we'll be here, we'll be staying connected, and the people who are not involved in this program, they can proceed to the auditorium.
But questionnaire sessions will be at end of this video?
Yes, this is true. Because when the videos will be going on, it will be difficult to stop it and to see the questions, right?
Good morning, friends. Welcome to IUAC and the fascinating world of accelerators. Here we will be showing you various accelerator facility and associated experimental facility when you go ahead in the tour. Let me begin with the oldest accelerator that we have at IUAC. This is 15 million volt accelerator, where at the cylindrical shell out here inside the accelerator, we can generate 15 million volts by Van de Graaff principle. And this high voltage is
Hello.
to accelerate the ions in million.
কোথায়?
This is a voltage.
12টা বাজছে তোমরা এখনো বেরোনি।
Stop.
Shomen, please mute yourself.
তোমাকে বলো কত দেরি আর?
Instrument called ion source, where we produce negative ions by attaching an extra electron to atom. This negative ion moves forward and they are bent by the magnet. This magnet not only bends the ion beam, but also ensures to select a particular ion of interest. For example, if I want to do experiment with say 28 silicon, the magnet ensures that only mass 28 goes through it and all other masses are rejected. The positive high voltage attracts the negative ion. So when the negative ion moves from here to here, it gets accelerated. When ions reach here, the energy is in million electron volts. Here we play a trick. What we do is, these ions are made to pass through a thin foil of carbon. And when they are passing through this thin foil of carbon, it loses many electrons and becomes positively charged. Now, once again, the ions are accelerated. But now, due to repulsion, positive potential, positive charge ions are repelled. Here, the energy gain is more. Why the energy gain is more? Because the charge is more. Remember, E is equal to Q into V. Higher the charge, higher the acceleration. The ion beam is accelerated. They are once again deflected using a magnet. This magnet ensures that the energy of all the ions remains same. A third magnet puts the beam into one of the 6 experimental facilities which are set up. So the experimental set up the facility in one of the setup, and the beam is going into it, and the experiment is conducted. So all the part of the ion beam is basically controlled from a control system out here. The control system, we are taking care of beam right from ion source to the experimental facility. We are not only producing the beam and putting it to the experimental facility, but also monitoring various parameters. There are around 400 parameters to be monitored at one go. The parameters like vacuum inside the chamber, the beam current, voltage stability, and the radiation levels. All are monitored using the control system out here. The accelerator is interlocked for all kind of hazard, like radiation hazard and the high pressure hazard. This ensures accident-free operation of accelerator and makes the operation trouble-free. Thank you.
So what we see here is the superconducting linear accelerator. Now this is a different kind of accelerator from the pelletron, in the sense that a superconducting linear accelerator uses AC voltage as against the pelletron, where a large DC voltage is used to accelerate the beams. This superconducting linac is basically a booster, energy booster to the pelletron accelerator, and it increases the energy of the charged particle beams that are coming from the pelletron. When this accelerator is operating at its maximum capacity, it doubles the energy of the beams that are available from the pelletron. So this accelerator basically consists of 5 modules. What we see here are the 3 accelerating modules where actually the acceleration is taking place or the increase in the energy is taking place. Besides these 3 modules, there is a super buncher module which is used for bunching, and there is a rebuncher module also which has the same function as the super buncher but which is used for bunching at the target location, at the experimental location. These modules, all the entire LINAC, at the heart of the LINAC is basically these structures. For the sake of clarity, we have kept one of them out. So all these modules are actually having these devices inside which are actually accelerating the beam, and they are known as the quarter wave resonators. So this is the quarter wave resonator from the outside, and this from the outside it is completely surrounded by stainless steel. So what we see here is not niobium but stainless steel jacket. This is the port from which liquid helium fills into the cavity, into the resonator. From here it fills into the cavity. The total length of this resonator is around half a meter. It will be actually 600 mm to be more precise. There are 4 ports, 4 openings. So these 2 lower openings are actually from where the beam charge particle enters into the resonator and leaves the resonator after acceleration. These 2 ports, one on this side and there is another one on the diagonal. These are known as the coupling ports, and one of them is used for coupling power into the resonator to excite it, to generate fields inside it, high voltages, and the other one is used for sampling small power out of the resonator to do measurements, to know what is the field that is existing inside the resonator. And as the name suggests, quarter wave resonators are basically electrical resonant circuits, electrical resonators which operate at a frequency of 97 megahertz. Now this particular structure is made up of niobium metal from the inside, and the outside is surrounded by a stainless steel jacket. Now niobium is a superconducting material and it becomes superconducting at 9.2 Kelvin. 9.2 Kelvin translates to minus 263.8 degrees. So when you cool down the niobium metal to minus 263.8 degrees centigrade, it becomes superconducting. So these resonators are actually cooled with liquid helium, which has a boiling point of 4.2 Kelvin. 4.2 Kelvin translates to minus 268.8 degrees centigrade. So these resonators are cooled to a temperature of minus 268.8 degrees centigrade, and hence they become superconducting. When they become superconducting, the benefit of using superconductivity is the tremendous power saving. The typical voltages at which these resonators operate, the accelerating voltage is of the order of 320 kilovolts. That is 300. generate such a high voltage. However, if we operate them in the normal conducting mode, for example, let us say we have a copper cavity which is not a superconductor and which operates in a normal mode, then to generate the same amount of voltage to accelerate, we will require powers of the order of 40 to 50 kilowatts. So you can see the tremendous advantage we have in terms of power savings when we use superconductivity.
The HCI comprises of 18 gigahertz high temperature superconducting electron cyclotron resonance ion source. There is a multi-harmonic buncher. After this radio frequency quadrupole operating at 48.5 megahertz, spiral buncher, which is again operating at 48.5 megahertz. And after this, there are 6 interdigital H-mode type drift tube linear accelerators, cavities to accelerate the ions. The high current injector is designed to accelerate almost all the ions, right from the beginning, hydrogen to the iodine, especially including the noble gases and metallic ions having a mass to charge ratio less than or equal to 6. The high current injector can accelerate up to the 6% of the velocity of light with higher current capacity. The current capacity is about 10 particle nanoampere. This current capacity is due to the multiple step ionization in the ion source, and which is very useful for the low cross-section reactions, especially for the nuclear physics experiment. Now, we'll talk about the different elements involved in HCI. So first I will talk about the ECR ion source. The ECR ion source provides the ions having energy of 8 keV per nucleon. And this provides the DC current, direct current, which is further bunched by the multi-harmonic buncher. And this bunched beam further will go to the radio frequency quadrupole. The radio frequency quadrupole is a kind of RF linear accelerator, and it has a 4-rod electrode having a length of 2.5 meter, and the bore diameter is about 12 millimeter. This can accelerate, this is basically designed to accelerate the ions from 8 keV to 180 keV per nucleon. Let us come to the 6 drift tube linear accelerators. These are all normal temperature RF structure, and this is basically the multi-RF gap structure. It comprises multiple gaps, multiple drift tubes separated by the RF gap. This whole structure will provide the energy gain from 180 keV per nucleon to 1.8 MeV per nucleon. There are various diagnostic components are installed in the beamline at the different places. The diagnostic components may be the Faraday cup, beam profile monitors, and others. So Faraday cup is basically used to measure the beam current, and beam profile monitors is used to measure the beam profiles at basically at the different locations in the beamline. Now we'll understand by taking one example. So suppose we are taking the silver ion. Silver has a mass of 107, and the HCI has a capability of producing the ions having energy is the 1.8 MeV per nucleon. And if you multiply the mass of the silver, that is 107, you will get the energy that is 192.6 million electron volt. So for silver ion, output energy of the silver ion is 192.6 million electron volt. And now this beam will go to the existing superconducting linear accelerator. At IUC that we are running 2 parallel accelerators simultaneously. One is the pelletron and another one is the high current injector. So that's the beauty about this accelerator at IUSC along with the other accelerators. Thank you very much.
The material science experiments are done in 3 beam lines. 2 of the beam lines are in the beam hall 1, and this is the 3rd beam line which you see here. So some of the conventional experiments we do in the beam hall 1, where the irradiation, general irradiation experiments at room temperature, liquid nitrogen temperature, and elevated temperatures are done. The irradiations for low fluence are also done there. We have 3 chambers in this beam line, and 2 are very highly specialized chambers, in which I will just give you in a few minutes. But initially I will show you this chamber. This is the conventional chamber where we do most of the irradiation experiments. This has a, as you can see from the top, you have a sample ladder from which the samples are mounted, and at a time you can mount up to around 24 or so samples at a time, and then irradiation can be done. The beams come from that side, that is the accelerator is on that side, and then these samples are irradiated here. What you see here is, this is a standard X-ray diffractometer. What is done here, this XRD, this is basically done for it. It is one of the fundamental techniques for doing this characterization of samples, where you can see the crystallization of the sample or its compound. This works on a very simple principle. What you have is what you see there is an X-ray source. The X-ray comes and falls here. There is some sort of a sample holder on which you mount your sample. This is mounted here. And then this X-rays are scattered, and this is the detector from where you get the diffraction pattern. And from the diffraction pattern, you see this is a standard formula 2D sin theta is equal to n lambda. You can get this spacing between different planes, and that gives you this what is the constant d, and you can get this idea of the element there. This is a standard system, but what we have done here is, as you can see, this accelerator beam is coming here, and then you can bring this chamber down, and this is connected to the beam. And then what we have is an in situ setup. What you do here is, like in the earlier chambers, you will have to take out the samples before doing this characterization in XRD. Here you can do it while the sample is still mounted there. So you can increase the fluence, you can increase the irradiation time without having to change the sample in between or having to take it out. So that makes it a very unique facility, because now you are not having the sample to sample variation. This type of setup makes it a very versatile, where you can do a lot of experiments which are not possible in any other. So this is the Raman system. So this is based on the Raman scattering system. You must have heard Dr. C.V. Raman got a Nobel Prize for discovering this Raman scattering effect. This is also one of the very conventional methods for doing this analysis of the mostly molecular elements. This is based on the system that a laser falls on your sample and energy is taken from that photon, and that shift is what you measure, which is called the Raman shift. So typically there is this is the vibrational band which takes the energy, and then this energy lowers. So this is what is used for this getting again information about the elements of your sample and this their state. What is unique now, if you look at on this side, this is the beam line coming. So this is our accelerator beam line from which accelerated beam through LINAC is coming, and then we have a chamber. So what is unique now here is that when the beam falls on the sample, there you see this chamber, which is a half cut chamber. So this is a specially designed chamber. So the beam goes inside and then falls on your sample, and then you have this collector. So you have, this is a half cut so that you can take the probe very near, and whatever signal is there, it comes through an optical fiber, and then it is fed into this Raman system. So again, this is a unique system because you are doing this Raman without having to take out the sample from the vacuum. So the beam is falling on your sample, and you can do the Raman while the beam is falling. So you can increase the irradiation without having to take the sample out and do the Raman measurement. So there are 3 chambers. First one we called Raman, in situ Raman, then a standard irradiation chamber, and the last one was the in situ XRD system.
The setup that you see here is the Indian National Gamma Array. It's a setup of gamma detectors. And in this setup, we study nuclei which are rotating at very high angular velocities, typically about 10 power 21. per second. In this, inside the scattering chamber, we keep the target material, which are bombarded by very heavy energy ion beams from the accelerator. And some of them, when they are above the Coulomb barrier, they fuse with the target nuclei. And we get a compound nuclei, which is formed at very high excitation energy and high angular momentum. This compound nuclei then decays by several protons or neutrons or alpha particles, and then it cools down. Once it cools down, it still has a lot of angular momentum and then some excitation energy, which further it cools down by emission of cascade of gamma rays. So it typically about 40 to 50 gamma rays are emitted in one cascade, and the aim of this detector array is to collect these gamma rays as efficiently as possible with high energy and time resolution. So this array, these detectors that you see are made up of high purity germanium crystals, and these have very high energy resolution. Now the gamma rays interact with these crystals through three basic processes: the photoelectric effect, the Compton scattering, and the pair production. In Compton scattering, most of the gamma rays only partially deposit the energy, and this causes a huge background in the gamma spectrum. To suppress this huge background, we use detectors which are surrounding the germanium detectors, which are called the anti-Compton shields. This improves the peak to total of the gamma spectrum. Now, what do we study? Once we see these gamma rays, we study various properties of these gamma rays, like their intensity, their correlation, their angular intensity distribution, and linear polarization. From these, we decipher about the quantum states inside the decaying nucleus. From these quantum states, we decipher about the various modes of excitation or de-excitation of the nucleus. And from that, we decipher about the properties of the nucleus. Now, when the nucleus decays and has a very high angular momentum, it tries to accommodate this angular momentum in various possible ways. It tries to change its shape, and the internal configuration of the nucleus changes a lot. So by studying the properties of the gamma rays, we could decipher about the shapes of the nucleus. So that's the basic aim. And from that, when the shape changes, there are very large changes happening inside the nucleus, and we come to know about the properties of the nuclei. Apart from the fundamental aspect, the gamma rays detector, the techniques of gamma ray spectroscopy can also be used for societal benefits. These are used, for example, in homeland securities and medical imaging, as well as trace elements of certain pollutants can be found out from soil and water using these techniques of gamma ray spectroscopy. So that's all. Thank you.
There are about 300 nuclei which are stable and which are available in nature, whereas there are several thousand, like about 7,000 nuclei which are unstable, which don't exist in nature. So the only way to study the properties of these nuclei is to produce them in the laboratory, and then within the fleeting short time that it remains before it decays, the properties have to be studied. Hybrid recoil mass analyzer, which is just behind me. So if you take a molecule, the atoms are bound in a molecule with a very small energy, whereas the protons and neutrons inside a nucleus are bound by million times more energy. In addition, if you want to study the reaction, nuclear reaction between any two nuclei, then you have to overcome the repulsion between the protons in the two nuclei. In order to study this nucleus, we take already studied light nuclei whose structure and properties are known, which are stable. We accelerated them to large energies, and then we bombard the species of the target nuclei, which is taken in the form of a foil or gas, and some of which will undergo nuclear reaction. The reason is the atom is mostly hollow, and the nucleus occupies a very tiny volume inside the atom. And the nuclei which we accelerate using large accelerator systems and bombard the target nuclei, they will go through hollow spaces. And only on some few occasions, they will come close enough in order to feel the nuclear force, which is strong and attractive, which operates only at a femtometer distance, 10 power minus 15 meters or so. And the strong attractive nuclear force can cause nuclei to undergo fusion or transfer or fusion fission. So the transfer reaction is nothing but exchange of some protons and neutrons between the projectile which is accelerated with the accelerator and the target which is taken in the form of a gas or a thin foil in the reaction chamber. And fusion is nothing but complete fusing of the projectile and target nucleus to form a very heavy nucleus which doesn't exist in nature, and which is hot and excited nucleus, and which can have a large amount of angular momentum also. So when we go to heavy systems, the fission is a very competing channel, and more often than not, the fused nucleus fissions in a very short time scale of the order of 10 power minus 20 or minus 21 seconds. So very few nuclei will exist in the fused heavy nuclear form, and these are hard to detect because the fusion reaction is the most difficult reaction in the sense that the projectile brings a certain amount of momentum, it fuses with the target nucleus, and then the compound nucleus which is thus formed due to momentum conservation moves in the forward direction. Now the probability of making this fusion reaction is very small. As I told you, the nucleus or the cross section of a nucleus is very small compared to the atomic cross section. So the fusion probability is very small, and in case it fuses, the compound nucleus can have a large angular momentum also. So we have this hybrid recoil mass analyzer, which is a dual stage, dual mode spectrometer. The first part of it starts from here. Inside this gamma chamber, there's a gamma array. There is a tiny vacuum chamber in which the target is put in the form of a foil, and the reaction takes place there. And the beam species, the accelerated beam particles, which are like trillion times more or a billion times more than the fusion reaction products, they all move together in the forward direction. So the background makes the biggest problem. And this electromagnetic device, the two stages, if we put together, it has electrostatic and magnetic dipoles for bending and for momentum and energy separation or dispersion. And we have large quadrupoles for focusing to increase the efficiency of the particles. And if we use the complete hybrid recoil mass analyzer, HYRA, which is two stages, both in vacuum, then we can carry out certain other reactions or fusion reactions in some other mass region in a different mode.
Dear students, let me introduce myself. My name is Sanish. So today I am going to give you a brief description about the neutron detector array at IUAC. So this array is called a national array of neutron detectors. This is the largest neutron detector array in our country and one of the few such facilities in the world. So let me divide this discussion into two parts. Initially, or in the first part, we will tell about the features of the array, structure and detectors involved, etc. And then the research program that we carry out using this multi-detector array will be discussed. So this array consists of 100 organic liquid scintillators mounted on this geodesic dome structure truncated at the bottom. And these detectors, like you can see, these detectors are mounted at well-defined or well-known spherical polar coordinates, theta and phi, and they are intended to detect fast neutrons coming from nuclear reactions. So two things we need to specify. Fast means how fast these neutrons are, and second thing, from where these neutrons are coming. This the energy of neutrons we expect here in the with the beam energies available at IUAC for this kind of reactions ranges from fractions of million electron volt, or in short MeV, to tens of MeV. So this is the typical energy range we deal with, the energy range of neutrons we expected in this kind of reactions. These fast neutrons, like 1 MeV neutron will take maybe 0.25 to 0.3 seconds. So they are that fast. Now from where these neutrons are coming? these neutrons are coming from the nuclear reaction that we conduct here. So for this, we mount nuclear targets and at the center of this chamber. This is a vacuum chamber for mounting our nuclear targets and other charge particle detectors like a fission detector or light charge particle detectors. And then the energetic being from our accelerator, Pelletron alone or sometimes Pelletron plus LINAC, that energetic beams we transport through the beamline and bombard onto the target. And we make the reaction to happen. And these particles, neutrons or gamma rays or other light charge particles, these all particles will be emitted during this collision process. And these detectors are used for catching maximum of such neutrons. Now, how we detect neutron? The detection principle is very simple. This is elastic scattering. In elastic scattering, we know when the masses of the colliding partners are same or similar, then we can attain maximum energy transfer. So with this, based on this, we select our detection medium such that the mass of the constituent element should be or nearly equal to the mass of neutron. So hence we select organic materials or organic compounds for the detection of fast neutrons as they contain hydrogen. This is one such detector. These all detectors are identical replicas. One fantastic property or one of the fantastic features of the detector is that they are sensitive to the kind of particle causing excitation. Or in other words, if the detector is illuminated with a neutron, then it shows one kind of signal compared to gamma. That means the detector signal, the output of a detector is a function or is a function of the kind of particle causing excitation. So we can exploit or we can utilize this feature to identify neutrons from other radiation background. That is very specific about organic liquid scintillators. So various institutes and universities in the country are part of this research program, and I hope to see some of you also coming in future to utilize this facility. Thank you.
Hello friends, my name is Sunil Oja. Here I will be demonstrating you one of the Van de Graaff accelerator that we have at IUAC. This machine can go up to 1.6 and it is a horizontal machine. Using this machine, we accelerate helium ions to do Rutherford backscattering spectrometry. This accelerator is used to perform same experiment which Rutherford and his group performed 110 years ago. I hope you all remember that Rutherford and his group used a thin foil of gold like this and they shot helium ions on this. To their surprise, what they saw, some of the helium or alphas came back. Using this experiment, we understand that atom is a hollow structure and whole its mass is basically concentrated on a small point called nucleus. So when this alpha goes very close to nucleus, they come back. And we can measure the energy of these alphas and know the constituent of the sample under observation. Let's see how this accelerator works. Here we have ion source, where we generate negative helium by first generating plasmas and then converting the plasma of helium into negative ions. These negative helium ions are then accelerated using this accelerator. Here inside we have high potential of 1 million volt. The stripper and high voltage is inside this tank. After stripping, helium ions are once again accelerated and the helium ions are then shot into the samples which are kept inside this chamber. A detector which is kept at a backscattering angle measures the energy of the backscattering helium. And because of that, we can get a spectrum which looks like this. Here we have plotted energy versus count of backscattered helium. Using this experiment, we can know the thickness of thin films or the composition of the films or the material under observation. Like if you see, this is the plot of a thin gold foil on silicon. And here we have an oxide of zirconium on a carbon. Thank you.
Hello friends, I am going to explain accelerator mass spectrometry facility at our center. So let us understand what is accelerator mass spectrometry. Accelerator mass spectrometry is basically mass spectrometry using an accelerator. So what is mass spectrometry? Mass spectrometry is a technique by which you can identify atoms or different molecules in a sample on the basis of their masses. So if you use accelerator for this purpose, then it is called accelerator mass spectrometry. Using an accelerator for mass spectrometry improve its sensitivity. Sensitivity of accelerator mass spectrometry is of the order of 10 to the power minus 16. What does it mean? It means that if you are going to identify one atom out of 10 to the power 16 atom, you can identify using this technique. Having such ultra high sensitivity makes this technique enable to measure long-lived cosmogenic radionuclides which are present in very low abundances in the local natural environment. Example of such radionuclides are 14 carbon, 10 beryllium, 26 aluminium, 36 chlorine, 129 iodine, etc. Most popular application of accelerator mass spectrometry technique is radiocarbon dating. So radiocarbon dating is a technique to measure age of old objects found in different excavations. Old objects such as woods, bones, charcoal, etc. Carbon has three isotopes, 12 carbon, 13 carbon, both are stable. 14 carbon is radioactive in nature. It decays with half-life of 5,730 years. When an organism is alive, all amount of all these three isotopes of carbon are in equilibrium with the atmosphere. But once an organism dies, amount of radiocarbon start decreasing because of its radioactive nature. One can measure remaining amount of radiocarbon in a sample. One can calculate the time period when that organism was died, or in simple words, he can calculate the age of that sample. Here I am showing you one block of wood. How much is the age of this? It is 48,000 years old. It is used as background sample in different radiocarbon labs. We have also measured this age of this sample in our lab using this our AMS system. So first we extract cellulose out of this wood sample, and the cellulose looks like this. And the cellulose is converted into graphite because our ion source accept the sample in the form of graphite. Graphite, it looks like this, very tiny amount, around 5 to 6 milligram. Now this graphite is loaded into tiny sample holder, which is also called cathode. Such 134 cathodes can be loaded in our ion sources. This source generates negative ions from this graphite sample, and we select negative ion of 12 carbon, 13 carbon, and 14 carbon using an injector magnet inside this box. These negative ions are attracted towards the positive potential present at the terminal of this accelerator. When these negative ions are passing through this terminal of accelerator, they are converted into positive ions by stripping some of their electron in a argon gas canal by stripping process. We select +1 charge state of 14 carbon, 12 carbon, 13 carbon using this analyzer magnet. Current of 12 carbon and 13 carbon are measured using 2 off-axis Faraday cup present here. 14 carbon is counted in this gas ionization detector. Finally, we take ratio of counts of 14 carbon and 12 carbon counts. And this ratio is converted into radiocarbon age of that sample. Thank you.
So this is high resolution secondary ion mass spectrometer. This is first of its kind in our country. And this is actually a large geometry secondary ion mass spectrometer with high mass and spatial resolution. And it also has high reproducibility. So there are a lot of questions about the evolution of Earth. And one of the question is this, that when the Earth was formed. So how to answer this question, how to know about when Earth was formed? So what we basically need to do is this, that we need to look for the rocks, which are very old rocks, and those are the rocks, they can answer this question. So inside, when the rock formation takes place, there is a mineral called zircon, and this is very, very robust mineral. It does not change or alter with the high temperature and high pressure, which are the condition when the earth formation takes place. So we need to look for this zircon mineral and do the zircon dating using this instrument. So what is there in the zircon? There is a uranium isotope inside zircon, and uranium is radioactive. Uranium 238 decays to lead 206, and uranium 235 decays to lead 207 with a different half-life. So basically, uranium acts as a clock inside the mineral, which is very robust. When the outer rings of zircon takes place, they also carry the information about the formation of that particular rock. So zircon, the score of zircon will tell when the rock was formed, and the outer rings of zircon will tell the further processes which happened during the formation of rock. So by knowing the parent to daughter ratio of these radioisotopes and using Concordia diagram, we can find out the age of the rock. So what happens in this instrument, we take the zircon mineral and then keep it in this chamber, where the zircon mineral is hit by the beams which are coming from the ion source. There are two ion sources in this machine, cesium ion source and oxygen ion source. So when this mineral is hit by the primary beam, the isotopes of uranium and lead, they come out of the sample and then pass through the electrostatic and magnetic separators and finally reach at the detection system, where they are simultaneously counted. And the process is so precise that all other neighboring isobars and isotopes are separated out by these filters. So by knowing the ratio of parent to daughter of uranium and lead isotopes and using Concordia diagram, we can find out the age of zircon. This is one of the application of HR SIMS. There are many other applications in nuclear particle detection and material science. Thank you.
Students, if you have any questions, you can put the questions in the chat box so that the presenters can give the answers.
Now people can unmute themselves and ask questions directly to the presenters.
We have
Everybody
yes.
has been unmuted.
And you have another session also, just another short video for small demonstrations of small experiments. So that will be followed by this questionnaire session. Or Abhishek, maybe you can start the presentations, another video. So maybe they can start typing the questionnaires in the chat box and the presenters can give the answers immediately through the chat box. So today I am going to show you the magnetic levitating racing track, which is one of the promising application of a superconductor. Superconductor has a basically a type of material which has a distinct properties, which is completely different than the normal material what you know, like copper or like steel or this kind of materials. Now, as you know, that normal material, so this is a resistance versus temperature curve. Okay, as you reduce the temperature, the resistance of the normal material keep on reducing, and then it stabilizes its one of at the finite value. So it doesn't reaches to the zero. Whereas in a superconductor, when you start cooling a superconducting material, initially it follows the same trend as normal material. So it will keep on reducing and reducing, and then beyond a certain temperature, the resistance suddenly vanishes and it becomes zero. Superconductor has also another distinct property. So you can see this red ball, okay, at normal temperature, that means at room temperature. If you apply a magnetic field, then all the field flux lines will pass through the superconductors. But if you cool that superconducting material to its superconducting states, that means you have to cool below its critical temperature. Then if you apply the same field, external magnetic field,
Introducing Speechula, the most natural sounding text-to-speech software on
magnetic flux to enter inside the superconductors. So it's a Meissner state. Now in this Meissner state, so the superconductor behave as a perfectly diamagnetic. So that means if you take a magnet, okay, normal magnet, if you place a superconductor on top of that, it will behave a diamagnetic. Okay, so that means it will create as if it is creating opposing field. Okay, it will repel to the existing field or external field. Okay, now I take one of the superconductor, which is yttrium barium copper oxide. You can see here, this is a ceramic type of material, and it is having the critical temperature of 92 Kelvin. 92 Kelvin. So that means if you want to make it a superconductor, you have to cool this material below 92 Kelvin. So to make it a superconductor, what we do, the nearest liquid we have a liquid nitrogen, which is having a boiling temperature of 77 Kelvin. So roughly minus 196 degrees centigrade. Now you think a diagram or three magnet north, south, north. So the magnetic flux line, what will happen? All the flux line from the north that will go to the south. So now if you place this YBCO material on top of this magnet, so there will be it will be trapped inside a flux. Okay, because so this will reorient the flux line because of its diamagnetic properties, and there will be a floating pockets will be generated on the top of this magnetic track. Now, if you have a series of such magnet, north, south, north. So if you have a series of such magnet, so you can think of a track. So there will be a floating path. So where the superconductor material doesn't have any contact with this path. So based on the same principle, you can see this is a magnetic track. It has a similar profile, magnet profile. So north, south, north. Okay. So now what we will do to demonstrate that magnetic levitations. So now this superconducting material generally embedded in a metallic envelope. This 1 micron layer is coated. Now just to demonstrate, so I have taken a small superconducting tape. So this is superconducting tape, what I have explained. I have taken a small tape. So I'll take similar one of the sample which is already dipped into the liquid nitrogen, and we'll put, now if you see, if I put this sample here, it's a normal, because now it is not in superconducting state, so it is not floating. Okay, so you can't do anything. Okay, now we will take one of the superconducting sample here. So it is floating completely. Okay, it's a floating, and almost there is a 3 millimeters of gap between this track and this superconducting samples. Now, if I give a small impulse, you can see if I give a small impulse, so it is rotating and it's a floating actually. So there is no friction between the track and the sample, and here it is moving against the gravity because the track is inverted. Okay, so as long as we can maintain the temperature, it will be moving. So based on the same principle, actually the magnetic maglev train was developed in Japan. So Japanese, they could achieve almost 600 km/h speed. You can reach actually Bombay or 2.5 hours. So this is one of the very promising application which is coming in a future, and some of the countries are already working on this kind of projects. Thank you.
Thermoelectric materials. Basically, thermoelectric materials are the materials which convert thermal energy into the electrical energy and electrical into the thermal energy. It means these type of materials can be used in both ways. There are two different type of effects to demonstrate this type of materials. First one is the Seebeck effect, in which we have two different type of materials, metal A and metal B, and if we make junction out of these two materials, suppose we put one junction as a hot and another junction as a cold. So in that case, what will happen? There is a voltage developed between across these two junctions, and that voltage is measured with the help of the voltmeter. So the voltage difference generated due to the temperature gradient delta T gives the Seebeck coefficient of that junction. Suppose we have two different type of materials. One is N-type semiconductor and another one is P-type semiconductor. Both are connected electrically in series and thermally in parallel. So if we connect our circuit diagram like that, that one side is hot and another side is cold, due to that temperature gradient, the charge carriers will move from hot side to the cold side, and due to the movement of the charge carriers, a power will be generated into the circuit and our bulb will be the glow. So now I am going to demonstrate how this heat can be used as a electrical energy. It is our actual thermoelectric module circuit in which we have two aluminum legs. These aluminum legs will supply heat or cold to our thermoelectric module, and using that module we will convert that heat into the electricity, and we will use that electricity to power over this fan. So now I am going to demonstrate this. Here we are putting normal water into this beaker, so it will act as a hot side for our this reference, and in another beaker we will put liquid nitrogen that will act as a cold side for our material. So we are putting this circuit into that. So this will act as a hot side, this will act as a cold side, and we are putting. So now you can see the fan is moving without connecting to a electricity. So how this fan is moving? We have created the temperature difference. One is hot, one is cold. The temperature difference across this thermoelectric module is giving you a voltage, and that voltage is going to be used to power this fan. So these thermoelectric metals can be used to recover waste heat into the electricity.
Hello everyone. Today I am going to present Van de Graaff accelerators. Van de Graaff accelerators or Van de Graaff generators, you can say, was first invented by Robert Jamison Van de Graaff in 1931. This machine has the ability to produce extremely high voltages. They can go up to few millions of volts. Using this high potential, the charged particles are accelerated to very high energies, which are used for doing experiments in physics. So, for this understanding of this Van de Graaff generator, you first need to understand what is static electricity. See, this is a glass rod, and if you rub it with your cloth, then it develops some static charge, and it can attract small pieces of thermocol balls. So Basically, what is happening here is that the atoms give up electrons or take up electrons depending on their nature when we rub it across any surface. So this process of electrification by rubbing is called as turboelectricity. Let's start with the construction of this machine. There are two pulleys, the lower one and the upper one. There is a motor which rotates the lower pulley, and the belt is moving across this, and the belt is rotating the upper one. So now here is a battery which is connected to the spray comb. This battery gives the positive potential, and the positive charges accumulate on these pointed ends. These positive charges produce a very high electric field, and the air around it gets ionized. So the air transfers this positive charge to the spray comb, from this spray comb to this belt, and this belt is continuously moving. So the belt carries the charge from here to the upper portion. A similar structure is available on the top side, where this spray comb picks up the positive charge and transfer it to the dome. Let's start this machine. This belt is continuously transferring the charge from lower to the upper portion, and this dome is charged. So now let's verify whether this dome is charged or not. This is a metal bowl which is connected to the ground, and when we place closer to it, a spark is occurring. You can see that. So what is basically happening here, when we put a metal bowl which is connected to the ground close to this, so this is very high potential, the air is getting ionized. So when we place it closer, the charges are getting discharged from here to ground. So this air is forming a discharge path. Take this thermocol bowl, put it here. Now this thermocol bowl is connected to this potential. So this is the complete body now. When I on these are having the same charges, and so they are repelling each other. These are some hairs. Turn it on and see.
The thing that you should know. Cannot.
What is happening here? The hairs are getting similar.
Even if
the similar charges
you're
are
not ready for the day, it can always be nice.
getting like this. So this is what happens when someone touches a charged body and gets goosebumps or hairs like this. This is all about this. We have learned today about the Van de Graaff generator. Thanks a lot. Hope you all are aware of the concept of radioactive decay of nuclei, and if not, we learn it through the process of our demonstration. Here I have 22 sodium radioactive source, which has a half-life of 2.6 years. This radionuclide decays via emission of a positron, which is an antiparticle of electron. And when this positron recombines with the electrons of the matter, surrounding matter, it emits two 511 keV gamma radiation or gamma photons. And because of the law of conservation of momentum, the two emitted gammas are 180 degree apart. So this is the setup to demonstrate the emission of the two 511 keV gammas after the annihilation of positron and electron. Here we are using two barium fluoride detectors to detect the two gammas, and the detectors are also perfectly aligned to 180 degree. As you can see, that since the detectors are perfectly aligned, that we are able to see two signals or two outputs from the detectors. This signifies that the two correlated gammas or the 180 degree emitted gammas are detected by the detector. Since the two detectors are perfectly aligned to 180 degree, we are able to see the two signals perfectly. However, any displacement or angular displacement of the detector would cause us to lose the correlation, and we would not have observed this signal. Now, you must be thinking, what is the application of this technique? So this has been used widely in the field of tomography, mainly the positron emission tomography. The setup is similar to what has been used here, except for an integrated set of detectors and a sophisticated processing and imaging technique. So, but however, for injection of the radionuclide into human body, we cannot use this particular source. So we use 18 fluorine source, which has a biological form of fluoro 2-dioxy glucose, and the minimum dose which is injected in the human body is around 5 to 10 millicurie. These specific sources are synthesized in the surrounding cyclotrons, and this particular radionuclide has a half-life of 109.7 minutes. But coming back to the experiment, as you have seen, there is this continuous bed of noise on which the signal is riding. So this noise is partly coming from the atmospheric cosmic radiation that we always live in, and the other reasons are coming from the scattering of the scattering, the accidental coincidence, and the scattered coincidence. So the accidental coincidence refers to the detected photons that are coming from a different recombination process, and the scattered coincidence is the photon detected after a scattering. So this 18 fluorine radioisotope has an analog of glucose. So it tracks down the consumption of glucose within the human body, because the cancerous cells have a higher tendency of intake of the glucose, and this is how we detect the cancerous or the malignant cells. You must have also heard of the CT scan along with PET. That technique is also very popular, and that is computed tomography, because the attenuation coefficient of gamma rays or the photons is different for different organs, and so it is required to correct the PET scan, and there we use CT scan, where gamma source of 511 keV is scanned across the body, and the PET scan is corrected with that image of the CT scan. That, having said that, that was associated with the oncology of the body. And coming to the neurology, I have a PET and CT scan result of a human brain, where you have a normal human brain and an abnormal human brain. So that the difference between the two can be clearly seen with where the flow of the glucose is strictly inhibited. So this is how the 18 fluorine radionuclide is used. And finally, this is not the limited application of this technique. There are other applications also in the field of research studies. Thank you.
Greetings to all. I'm Golda. I'm working in the field of nuclear physics. On hearing the word nuclear, people become panic. Why is it so? It's because actually because of the satanic outcomes of nuclear weapons or nuclear accidents that had happened in the past. Because of those effects, when we hear the word nuclear, we all become very cautious. But we don't have to worry much, because in our day-to-day life, we are directly or indirectly making use of nuclear physics or nuclear technology everywhere, every sphere of our life, like in medicine, agriculture, industry, and so on. So the radiation can be alpha, beta, and gamma. Alpha is nothing but the helium nucleus. It has 2 protons and 2 neutrons. And beta is high energy electrons. And gamma is very high energy electromagnetic radiation. So as far as the radiation is concerned, so we are bothered about the biological effects of it. When we are talking about the biological effects, we are concerned about the ionization property, or in a way the penetrating power of the radiation. For the penetrating power is inversely related to the ionization property. You know, we have a radioactive source and a nuclear radiation detector right on the ceiling of our house or school, cinema theater or shopping mall, etc. These are actually used for detecting the presence of smoke. So, there are mainly two types of smoke detectors. One is photoelectric and another one is ionization type. The ionization type, it has a radioactive material in it, and it also makes use of nuclear technology for the detection. It has a ionization chamber with a radioactive source in the vicinity. Here, in case of normal smoke detectors, we use 241 americium. It is an alpha emitter. The quantity of the material used in the smoke detectors are very less. It is about 0.2 milligram. How does it work? It has a ionization chamber where here air is acting as the media of gas. So you apply a voltage across it, and the source is kept here. For source is emitting radiation, alpha particles. These alpha particles ionize atoms in the air. The negatively charged ions produced there will get attracted towards the positive plate, and the positive ion will be attracted towards the negative plate. For now, let us see. This is the internal part of the ionizing type smoke detector. This is the ionization chamber part. Within that, there is a hole, and below that, the radioactive material is placed. Here it is americium 241. So it is continuously emitting alpha particles and ionizing this region, the air within this region that you see here. So means the ions, the air in this region is getting ionized, and the electrode here and on the back side is getting is collecting the ions produced here, and a continuous current is going through. But when there is, say, smoke, then that is, the current is stopped or it is running. Let us see. Yeah, how we make use of nuclear detector and radiation techniques in our day-to-day life.
So hello everyone. Today I am going to demonstrate you that how resistivity of a material varies with the temperature. So let's start. So first of all, what is resistivity? Resistivity is a property of a material by which it opposes any motion of a charge passes through it. Okay. The unit of this is ohm meter, and on the basis of this resistivity value, we can divide matter in basically in three categories. One is conductor, other is insulator, and then semiconductor. Okay, so these are some example of copper and aluminum, which are the metal. You can see here the value of this is around approximately 10 raised to the power minus 8 ohm meter. And silicon, which is a semiconductor, for this value is 10 raised to the power 2, and for the glass, which is an insulator, its value is 10 raised to the power 11. So first I will demonstrate you, then I will explain that how this variation is different for metal and the semiconductor. So now let's first consider the metal case. So this is small circuit. Here we have a 9 volt DC power supply, and then this is the bulb, this is the switch, and here we have a copper coil. Now if I close this circuit, then current should flow through this circuit. If the current is sufficiently high, then this bulb should glow. So now let's see what happens if I close the circuit, then this bulb is not glowing. What does it mean? It means that the resistance offered by
this coil is sufficiently high so that the current flowing in this circuit is low and this bulb is not glowing. So now what happens if I reduce the temperature of this particular coil? Here we have liquid nitrogen. Temperature of this liquid nitrogen is 77 Kelvin. It is well below the room temperature. Now if I put this coil into this liquid nitrogen, then what you will observe, then this bulb will start glowing. What does it mean? It means that as we are going down in a temperature, then the resistance of this particular coil is reducing and hence the current is increasing and this bulb will start glowing. Okay, now let's move to the other part, which is of semiconductor. Here similar kind of a setup is here. Here instead of bulb we have a LED, and instead of the copper coil we have a thermistor. It is a semiconductor. So now if I close this circuit, then at room temperature what we observe, this LED is glowing. It means that at room temperature the sufficient current is flowing to light up this LED. Let's reduce this temperature of this thermistor, and what we will observe, that it stopped glowing. It means at the lower temperature this thermistor is providing higher resistance to this circuit so that it is not glowing. So what you can see, that in case of a metal, from this graph, if we are reducing the temperature, the resistivity is decreasing. In case of the semiconductor, if we are reducing the temperature, then resistivity is increasing. So this is all for this concept. Thank you.
So the aim of the experiment is to demonstrate the total internal reflection of light and the how light can be bent at the curvature, and it can be reflected at the interfaces of the medium and travel along. So this is the point to be noted is this is the main working principle of optical fiber communication that we are experiencing in our day-to-day life today. So the main working principle of this experiment is to make you understand that light, when it is traveling from one medium to another medium, it bends away or towards the normal. So if it is moving from high refractive index medium to low refractive index medium, that is from a denser medium to a rarer medium. Here we can have water as a denser medium and air as the rarer medium. So it basically bends away from the normal. So how we actually discuss this effect of total internal reflection is when the incident angle that is appearing at the medium interface, if it is increasing beyond a certain angle of incidence, it tends to bend away from the normal, and at a particular angle of incidence, which is known as critical angle, it becomes parallel to the interface, or it is normal to the it is perpendicular to the normal at the interface. And when it is going beyond that angle of incidence, it bends into it gets reflected into that medium itself. So as we can see here in this diagram, when the angle of incidence in the green ray, we can see when the angle of incidence is certain angle theta, which is less than a critical angle, it gets refracted away from the normal, but it is not getting perpendicular to the normal. When the red wave we can see it is getting perpendicular to the normal, so this particular angle is the critical angle, and the blue one, which is more than the critical angle, it shows that it gets reflected totally inside the medium which it was coming from. So this critical angle is governed by a popular law called Snell's law, and it is known as, it is basically this sine inverse of the refractive index of the denser medium to the rarer medium. What I mean by refractive index is, refractive index basically tells us about the speed of light, which is when it is traveling through the medium. So it is governed by the ratio of the speed of light in vacuum or air to the speed of light in the medium. So certainly the light travels slower in the mediums than in comparison to the vacuum or air. So that makes this number refractive index greater than 1. So here we have got, in our experiment, we have got water as the denser medium whose refractive index is around 1.33, and the air which is treated as the refractive index 1. So in this experiment, as we can see in this picture, the setup shows we got to have a laser, which is our light source, which is a very narrow band light source. Then we got to have a beaker or a bottle or a jar with a water with a hole at certain level so that we can pass the laser light through it. And then we got to have an empty beaker to pour the water into it. So how we are going to perform the experiment is that we are going to focus the laser on the opposite side of the hole in the water bottle, which is filled with water, and we are going to have a beaker which is empty where the water is going to come, and then we are giving you a screen where we can see how the light is bending. So let us start the experiment. Here we can see the light is now straight, like it is a little bit bent, but it is not following because there is no water flow, so it is not following anything. So at the interface of the air and water, we are getting a little bit bending away from the normal, which is like this. So when we are going to let the water flow, so this spot has gone, there is no light here, and I can show you that the light is following my hand. So the light is basically following the flow of the water. So the light is bending here at this point, and then this point, and this point, and this point. So this way it is getting totally internally reflected at every interface that it is having water and air. So we understood here that how the light bends at the curvature, how we can use this light to transfer information from this point to this point following a medium. This is basically typically what happens in case of an optical fiber, where the light is fed into from one point and it's taken from the glass based material through several distances, and it maintains the flow of information in a very secured manner. Thank you very much.
Hello friends. So today we are going to demonstrate the principle of gyroscopic effect. A gyroscope is a device with a spinning wheel or spinning disc, and it harnesses on the principle of preserving the angular momentum. And as we know from Newton's law that if we apply force to a body, it will try to increase the momentum of the body in the direction of force. So similar happens when it comes to the angular velocity. So if we want to change the angular momentum, then we need to apply a torque. So for that, in the direction of torque, there is a change of the angular momentum. Now this simple device actually, it has a tendency to protect it from any change of the angular momentum if it's subject to a external torque. Now this simple device actually can create a extraordinary effects which is used in almost in every navigation system like aircraft, like ships and rockets. So without spin, so this is a gyroscope actually, this is a model of gyroscope. Without any spinning, the device does not have any significant effect. But whenever it is subjected to a angular spin, it actually offers two properties. One is rigidity and second one is precision. So due to this rigidity, actually it opposes any change in the direction of the spin angular momentum, and due to precision and due to this OS, actually it rotates around the pivot, and it defies the gravitational effects. So we'll demonstrate it with some few of our experimental arrangements. So first, this is our gyroscope. This is a simple, you can see this is a gimbal kind of structure, and it rotates around this axis. So what happens if we don't give it a spin? So it just, if we want to place it on a pedestal, it just falls down.
Abhishek, can you hear?
Yeah, I think it has to be loaded again, right, Shobhan?
We'll
I don't know
provide
how
a
it went off.
into this structure. So now you can see it actually stabilized it, and it actually defies the gravity. Whenever there was a spin, it actually defies the gravity. And how it happens? So you can see. So this is the direction of the angular momentum. So when the weight the
Something is wrong. Getting disconnected again and again.
that torque works in this direction. As a result, when it's spinning, it has a
Abhishek,
precipitation
Sahu, can you just see?
torque, and as a result, it defies the gravity. So we can demonstrate this in a with the bicycle wheel also. So this is our bicycle wheel, and this is a motor. So with this motor, we'll provide this bicycle a spin.
Sahu,
See that without the spin, if we don't give this bicycle wheel a spin, then if we want to hang it by rope, then it just falls down. So now what we will do, we'll give it a angular momentum with this motor. So now you see, so this actually defies the gravity, and it actually presses around this rope. We'll try to demonstrate how the rigidity of a gyroscope actually stabilizes the whole system. To show the rigidity of a gyroscopic device, what we have used, this is a disc, and this is attached to a CD. So this disc is actually free rotating. Now we have at the back side of the CD, we have used a motor. This is any kind of simple motor that is used in any kind of toy, and this is run by a 9-volt battery. So now when we switch on this disc start rotating. Now if we want to place it on a table, it just falls it down. But when we give it a spin, so it stands. Not only it stands, if we want to disturb it, it does not fall down. So this is an extreme rigidity that is shown by gyroscopic effect. And because of this rigidity, this gyroscope actually used any kind of spacecraft, rocket, and ships to give it a particular direction of navigation and a particular rigidity. So gyroscope is a extremely useful device which are used in our everyday life, and it is all mainly based on the principle of conservation of angular momentum. Thank you.
The video has been ended. Yeah.
So
People can
students,
ask
you can ask questions. You can put it in a chat box, or you can send the questionnaires also in the to the mail also, and the mail given by Dr. Ghosh, I think. So
people can turn on their videos also.
So students, the video what we have seen, because there is no end of this kind of questions, I know. So the videos what we have seen, please, if you have a specific questions on the videos or on our facility tour of IUAC, that will be... Yes, please. But please be specific to the videos what we have showed you. Okay. Ambuj, you are there? Ambuj?
Which Ambuj you are referring to, you sir?
Ambuj Tripathi, I believe.
Ambuj Tripathi or Ambuj Misra?
Yeah, Ambuj.
Sir, I am there
Ambuj,
on his behalf.
Acha, okay, okay. So, could you please take some of the few questions, right? In case of superconductor, the electron are ordered a different configuration forming Cooper pair. So, what is Cooper pair? Saif, could you please just say few liner? Yeah, very quickly.
Sir, I think Somen sir can answer this better.
I
Dr.
think
Soman has already written some.
Already written it. Okay, okay, okay. Okay, so there is another question. Bappa, Bappa already has written, can gyroscopic effect be used in vehicle's wheel?
Yeah, I have already answered actually.
Okay, fine. So, Abhishek, the students can ask the question vocally also, orally also, right? By using their audio.
Yes, sir. People can ask questions because everybody is unmuted.
Okay. So there are so many questions. I'm just going.
And I request people to switch on their videos so that we can have a group photograph or some kind of this.
Okay. Please switch on your video also. Showman, there is a question of liquid helium which 2 has 0 drag. So how is the liquid helium manager exactly? What does it mean?
Just a minute. Let me see the questions. Where is that question?
At 1317.
1317 mein there is a question also. Ek baar dekho.
Oh, so liquid helium also 0 drag. So how is it? I believe he is suspecting, he is referring to the superfluidity, I believe, because superfluidity is where you don't have generally any liquid has some kind of a viscosity. So viscosity is basically layer to layer frictions between the liquid. In case of liquid helium, when it goes below to certain temperature, basically it goes to a quantum transition. So there is no friction at all. So it's a quantum liquid actually. So that time you have an infinite conductivity of this one. So through a narrow channel also you can send a huge amount of liquid helium. But for that you need to bring down the temperature much below than the 4.2 Kelvin. So that's why it's 0 drag, I think telling. So there is no viscosity. So there is no friction between the one layer of liquid helium to another layer of liquid helium. So it becomes a superfluids. Because the fluid has like superconductor has a resistance and superconductivity material doesn't have resistance. Similarly, fluid has a viscosity. So and superfluidity doesn't have any viscous properties.
Okay, so there is another question also that the critical temperature niobium is 9. Achha, you have answered this.
I have answered this actually.
Yeah. Liquid helium with
many of the questions are already answered.
I think most of the questions have been answered.
Okay, so to cut short this session, so could you please ask the question by using your audio mic?
Now students can unmute and I think they can ask the questions.
Anybody can unmute now. We have given the privilege to everybody, right? So.
Yes, sir.
Actually, all the questions in the chat box have already been answered. So unless there are new questions, I think the session is coming to an end. Subhendu, you can ask some students to give feedback.
Yeah. So if you have any kind of feedback, any kind of suggestion, so that we can improve ourselves, the quality of the program in next year, so you are most welcome, and you can send it us your feedback. Teachers also, especially the teachers, if you think something can be improved from our side, so please let us know by writing to us by using that email address, which is iuscprocom@gmail.com, right? and all the registered students will be sending the e-participation certificate along with their names and the name of the schools also, I believe. So please write to us for any kind of suggestion, and I will appreciate if some of you can put on the video, please, so that we can take a snapshot, we can take a picture. एक बार थोड़ा कैमरा ऑन कर दीजिए.
ऑन करो
हैं?
कैमरा. अब क्या करें?
जिनका possible है, please you can switch on. If you feel it is not possible, then you can switch it off. Don't worry. Those
Now
who
we
feel
have to squeeze this thing now to make everything in a frame.
Yeah, actually, people need to just switch on their video.
Okay, so there is, I think, see teacher Gauri Roy. You want to say something? Please unmute.
I think the students or teachers who would like to switch on the video, you can switch on, or otherwise you can keep
Yeah,
it off.
Soman, there is a feedback. Please, let's. Yeah, please unmute and speak. Gauri Roy.
Miss Roy, you want to say something, please? You can unmute yourself. Do you have any problem? You are not able to unmute yourself? Okay, I think that she is probably having some problem. So in any case, if you want to have any suggestion, please. Miss Roy, you want to say something?
You can write in chat box in case you are not able to.
Yeah, we can see you, but we are not able to hear you.
So there are others like Dhruv Sahagal.
Okay, so Sao, you can take a picture of the screen snapshot by squeezing this. At least the names will be appearing. Unable to unmute.
Yeah, already we have taken.
Why she is unable to unmute? You give the permission to Miss Roy.
We have allowed everyone to unmute.
Yeah. A very good afternoon to one and all. It was. Am I audible now?
Yeah, you're audible. Yes. Go ahead.
Am I audible?
Yes, go ahead, please.
Audible. We can hear you. It's okay. Please say.
Yes.
We can.
Somehow I'm not audible, most probably.
No, you are audible.
It's okay.
No, you are audible. No problem. You are audible.
I cannot hear my voice. That is the thing.
Oh, we can hear you.
We can hear you.
Keep on speaking.
Please tell. Yeah, Shobin has written, we can hear you. So please go ahead, ma'am. We are putting the message in the chat box also.
Yeah, I think students have, all the videos are on now. Now, sir, you can take the picture.
Okay, so how you can take the picture now?
Yes, sir.
Because others are waiting.
Yes, sir.
Miss Roy, we can hear you. You can go ahead and you can
No,
speak.
there was some problem. Actually, I had connected my speakers to hear it clearly, and I forgot to disconnect the cord, so it was not coming.
Bataiye.
I'd like to give my feedback in terms of it is always a very good and a very very encouraging initiative from your side to conduct a program and involve the school students in that, and the students really learn a lot by these experiences which you share with us, and especially the keynote lectures. Like last year also we had a very good keynote speech, and this year also. So I'd like to thank from on behalf of my students, my school and myself for this initiative. Sir, I have one small thing to ask, like suggestion. This liquid nitrogen we use like for many experiments. Like, do you suggest like having this liquid nitrogen in the school laboratories? What do you think about that? Usually we don't have it.
Yeah.
Usually we don't have it, sir.
No, actually, in the past, when the school used to come to visit us in our institute,
Yes,
we used to get a lot of requests to supply the liquid nitrogen, and we have supplied a few schools also. But there
Okay.
are a few problems because liquid nitrogen is, you have to be very careful to handle it. If it is
Yeah.
falling on your hand, you will get a severe cold burn.
Okay.
So that probably is not recommended to give it to the students because any accident can happen.
Okay.
Showman, you can answer because he's some sort of a in charge of the cryogenic lab. Showman, could you please answer that how we can supply the liquid nitrogen to the schools under the supervision of some teacher?
Yes, probably if you are in Delhi, you are always welcome to visit IUSC and have a look, and you can do small funny experiment with your students. I think anytime that's welcome. In school, though liquid nitrogen is actually much cheaper than your water bottle, so it comes around 10 rupees per liter because
But
it's
they,
abundant in a atmosphere.
but
But
they
still,
cannot.
because of the cryogenic temperature, so it has to be certain, you need to follow certain kind of a safety procedures, especially when you are exposing this liquid to the students. So you can easily get it, but you need to take a lot of precautions to handle this. And it's a 10 rupees per liter, so you can, there are a lot of suppliers, you can get it, but you need to follow all the protocols, safety protocols. But if you're in Delhi, please come to IUSC. You can anytime, you can have a look, fill of liquid nitrogen. You can just dip some flowers or something, and you can see how they are
Yeah.
basically.
Many
So it's,
interesting experiments can be done. Is that means it is available? Like we can procure it from the shops which
oh yes, you
provide
should
us
have
this
proper
type of-
containers for that one, and not shops. There are some liquid nitrogen suppliers, are big suppliers are there.
also supply. Yeah.
You may not get in a small quantity. That's another problem. So
Okay.
because they don't provide in a small quantity, because it is cheaper than the your mineral water. It's a 10 rupees per liter.
All right.
But the 10 rupees per liter when you buy in 5,000
No,
liters,
it
right?
depends on the cities actually. In
Okay.
Delhi, definitely when you buy a small quantity, it will be much higher. But I'm telling
Yeah.
overall, it's a cheaper than ye. But because of this cryogenic temperature, it is not advised to use in school levels. So
Okay.
it has to be under supervision of some experts.
But
Thank
ma'am, we don't sound to be very negative. If you want to have some kind of a liquid nitrogen, you are most welcome to contact us. I believe that we know you. You used to come to our lab also. So you can write to us and we
I
will try
think
to see if we can provide it to you in a small
no, sir.
quantity.
I'm much far away from Delhi. I'm nearer to Bangalore. In fact, near in Mysore. So I'm in Mysore along with my.
This is another
So,
Miss Roy. Okay,
yeah.
okay.
So I can always get in touch with many other organizations which we have nearby us. So we can always request them. Only the thing is that it should be handled properly and dealt with.
Yeah, yeah.
Thank you.
You can get this liquid nitrogen from any food processing industry if it is nearby, or some animal husbandry, I think, or any biological preservation lab. Suppose stem cell
Right.
preservation, all
Yeah.
these things. So they all use liquid nitrogens actually.
Yes, sir. So
And
in
in
Middle,
fact,
there was a short period where ice creams were being made
yes,
with
yes, in the food
frozen
industry
with
also, a
liquid
lot of people
nitrogen. Food
used
industry was using it a lot.
liquid air actually. That they use the liquid air. So
Okay.
almost.
Okay, sir. Thank you.
Okay, so now it is almost 1:40 and people are probably very hungry. So we can conclude it here. And thank you very much all the students and teachers to join us. And we look forward to have some more interaction with you through email. Please write to us if you have any question.
Excuse
Okay?
me, sir.
Yes, yes. Go on.
May I say something?
Yes.
Yeah, please.
Yes, sir. So, sir, everything was quite good. I understood everything. The physics aspect and the chemistry aspect was like very extravagantly explained. I was looking forward to more of the biology aspect. I'm not saying that it was not really there. I picked few tricks from here and there, but getting into more of the interaction, the collaboration between physics, chemistry, and biology all together would give it a very good shape.
Yeah, that's
We
a
have, I think, radiation. Maybe we have some biology also, biological. So maybe you can speak something on.
Yeah, we are actually mostly
Biological cells.
focused on the physics part, the experimental physics part. But we are having one dedicated department which is dealing with the radiation biology. So you have heard about it, right? If you are having a cancerous tumor and if you put this ion beam, So it will destroy the cancerous cell, right? It will basically damage the DNA, it will break the DNA, and it will start killing those kind of cancerous cells. So those kind of small research is going on in our laboratory, but it is not a full-fledged biology. You know, it is not having the botany or some kind of a physiology or this kind of thing. It is only focused towards the radiation-related biological effect on the cells and other things mostly. So yes, it is a good scenario. So in future, it is a good suggestion, and in future we'll try to include one small talk about the biological research what is going on in our center. So thank you very much for your suggestion.
Yes, sir. Thank you.
Anybody else, please?
Good afternoon, sir. This is Smriti Gupta. I
Yes.
have been, I have been visiting IUAC for the last consecutive 6 years, I believe. The previous 4 years were for, it was physical, and the last 2 years it is virtual because of, the situation. Every year as a teacher, I am a teacher, and every year I am learning the new things from this IUAC. And I would really appreciate that, nowadays CBSE has deleted the nuclear reactions from class 12 point of view. I'm a chemistry teacher. So I am sure that the students might have learned about the alpha, beta, and gamma rays today, and, gold foil experiments that have been shown to the students today. So I am sure that the students might have learned a lot of things from what has been delivered. Thank you so much, and I believe that next year we'll be definitely going physically to IUAC and learning so many things again. Thank you, sir.
Okay, you are most welcome. So we'll invite the people from Bangalore also, right, Miss Roy? Okay. Okay, so if there is no further question, so let me once again thank all of you, my colleagues, teachers, students, and please write to us if you have any question. Okay.
One thing, Subhendu, I think the online mode has made it possible for us to connect every corner of India actually to this others. Because physically, mostly Delhi school participate. I think next year onwards, you have to keep it if it is in a dual mode, so that every corner can also can join along with the physical presence of the EA. So
hybrid mode.
Hybrid mode. So
we will try next year in the hybrid mode.
I think that will be because like she is joining from Bangalore. She's joining from Bangalore.
Yes, ma'am. Yes.
But do give us a chance to visit you all who are
Oh,
not
that is always
in the
welcome.
vicinity.
That is always.
No, even if you want, we can send the liquid nitrogen to Bangalore also. Okay. Okay, so it was nice to interact all of you. So thank you very much.
Thank you.
Bye.
Thank you all.
Now I cannot leave the meeting also. What